Hello everyone, welcome to the channel of Algocamp. So in this particular series, we are going to start talking about a few interesting concepts around data structures and algorithms. These videos are going to be power packed with in-depth explanations, problem solving around some very important aspects of data structures and algorithms. DSA is one of the most important topics when you see software engineering interviews for both internships roles and full-time roles. And I see that a lot of people actually struggle with that. So in this particular video series, what I have tried is I have tried to make sure that I try to solve the problems and try to explain the corresponding concepts with a more intuition building kind of like a scene. And we will be doing a lot of pattern based problem solving so that you can actually see what kind of problems can be solved with a specific type of algorithmic pattern. In this particular start of the series, we are going to actually start with searching algorithms. I believe searching algorithms are one of the most important algorithms if you want to actually excel in DSA, and a lot of advanced concepts in DSA do rely on searching algorithms. So without any further ado, let's just start this particular video, but I would highly encourage you to do subscribe to the channel if you have not yet subscribed, because we are going to put some really awesome content coming up ahead, and all of these videos are going to be really helpful for you for preparing for your next software engineering interviews. So let's just start. So now we have learned a lot of things around in binary search, and we have a good amount of knowledge base also that exists with us for binary search, right? Now in binary search, there are some specific type of problems called as minimax problems of searching, right? What are these minimax problems of searching? Let's try to talk about it and let's try to understand them. So at a lot of times I said that whenever you get a problem where you have to calculate minimum of something, maximum something, there are multiple techniques. Searching can be, or binary search can be one of those. Apart from this, in a lot of questions, you will find a term that minimize the maximum of a value or maximize the minimum of a value. Okay. So you'll be given some quantity, and the question might ask you to minimize the maximum of that quantity or maximize the minimum of that quantity. These kind of problems you might encounter. These are called as minimax problems of searching. There are one more type of minimax problems that exist, but that is more or less related to game theory and all. But in minimax problem of searching, you will be given some value or some quantity, and you might be asked to minimize the maximum of it or maximize the minimum of it. It might not look that intuitive in the first go, but let's try to take an example problem. With that example problem, we'll try to understand what actually they mean here. So there is a very famous problem from Spoj named as aggressive cows, right? What the problem says that Farmer John has built a new long barn with n stalls. Okay, so we have a new long barn, and inside this barn we have n stalls. Okay, we have n stalls, 1 2 3 4 n minus 1 n, right? We have n stalls in this barn. N can be as big as 10 raised to the power 5. Barn is kind of like a dairy. Okay, n is as big as 10 raised to the power 5. The stalls are located along a straight line. So you can see I have also marked all of the stalls in a straight line at positions x1, xn, and so on, right? So there will be multiple stalls. So let's say one stall S1 is here, S2 is here, then S3 is here. There will be multiple stalls, and the positions of these stalls will be x1, x2, x3. These stalls will be present inside this barn only, right? These stalls will be present inside these barns only. His C cows don't like this barn layout and become aggressive to each other, right? So there are total C cows, right? And they are very aggressive towards each other, right? To prevent the cows from hurting each other, Farmer John wants to assign the cows to the stalls such that the minimum distance between any two of them is as large as possible, right? So now you need to place the cows in the stalls. You need to place the cows in the stalls such that the minimum distance minimum distance between any two cows is maximized. Now you can see we are somehow having a quantity like distance between two cows. We have to maximize the minimum of it, right? What do they say? They say that calculate the value such that the minimum distance between any two cows is maximum, right? Or is maximized. So you want to maximize the minimum distance between any two cows. This is what the problem actually asks for, right? So now we have n stalls. These are different stalls and we have been given positions of the stalls, right? We have been given positions of the stalls. In these stalls, we are going to put some cows. There will be C cows that you need to put. You need to place them as far as possible such that the minimum distance between any two cows is maximum possible. So let's take an example. Let's take an example and then we will be able to understand. It says T test cases, followed by in every test case, there will be a value N and C. So what does N represent? Number of stalls. Okay, so there are 5 stalls. Okay. How many cows are there? There are 3 cows. There are 3 cows. And the positions of the stalls are 1, 2, 8, 4, 9. Positions of the stalls are 1, 2, 8, 4, 9. So if you actually see, this is position 1, position 2, position 4, position 8, position 9. Okay. Something like this. So we have 2 stalls, then we have a stall after one more distance, then we have after a few more distance, we have 2 more stalls, right? So this is the layout of the whole barn, that you have 5 stalls. The first stall is at place 1, second stall is at place 2, third stall is at place 4, fourth stall is at place 8, fifth stall is at place 5. So you have 5 stalls on these 5 positions. And what you need to make sure is these C cows are as far as possible. You need to compute an algorithm such that you are able to place the cows as far as possible. That is why they are asking you to maximize the minimum distance between any two cows. Okay, this is what they are asking for. So what can be a good, I would say, representation? Now one way to put the cows is you put C1 here, C2 here and C3 here. This is one possible, I would say, arrangement, right? That you have 5 stalls, you have 3 cows, you just place all of them like this. Now, what is the distance between C1, C2? Distance between C1, C2 is 1. What is the distance between C2, C3? Distance between these two is 2. What is the minimum distance between any two cows? 1. Right? So, one candidate that you get is 1. That minimum distance in this arrangement, if you arrange cows like this, then the minimum distance between any two cows is 1. You have either one distance between each cows or greater than 1 in this representation. But we can do something better. What we can do is we can say, let's say C1 here, C2 here, and let's say C3 here. Now let's see, what is the distance between C1, C2? 3. What is the distance between C2, C3? 4. What is the minimum distance between any two cows? 3. So this is another candidate that in the second type of arrangement, the minimum distance between any two cows was 3. Let's try again. Let's try with another configuration. C1, C2, C3. Here also the distance between C2 and C1 is again 3. But the distance between C3 and C2 is 5. What is the minimum distance between any two cows? The minimum distance between any two cows is 3. So 3 remains as it is here. Let's do another rearrangement. Let's do something like this. Minimum distance between C1, C2 is what? 7. But minimum distance between C2, C3 is 1. Right? So minimum distance in this arrangement is what? 1. And so on. There will be multiple such, I would say, combination. For each combination, you have noted down the minimum distance between the cows in that combination. What you have to do? You have to return the maximum of it. What will be the maximum of it? Can I say 3 will be the maximum of it? And if you see, the answer is also 3. That in any rearrangement, there is only one rearrangement such that the minimum distance between any two cows, there will be let's say 100 cows. If you see the adjacent distance between all the possible cows, then the minimum distance between any two cows is going to be this 3, right? That's what the problem is asking for. So you will be given the barn layout, you will be given the number of cows, number of stalls, and positions of the stalls, and you have to figure out what is the, I would say, maximum value for the minimum distance between any two cows. This is the problem statement in hand. Now, how can we actually solve this question? And now we are able to visualize that this is a minimax problem. How can we apply binary search here? So application of binary search is going to be easy if we have already done the problem like painter partitions and like binary search on answer. It's going to actually eventually, I would say, look like a binary search on answer like a problem only. Okay. Now, if you see here, let's say we were having only two cows, because if there is one cow, then of course there is no point, right? At least two cows will be there. If we have two cows, then just think about it. What can be the minimum distance between any two cows? The minimum distance, I can say that if there is a case that the first cow is placed at the first stall and the second cow is placed at the second stall, then whatever is the difference between both of them, that will be the minimum distance. Can I say that? Or whatever adjacent, closest adjacent pair value you have got, right? So for example, if you have this as 3 4, then this 3 4 will give you the minimum value that you place a cow here and place a cow here, right? So what I can say is that in some case we will definitely get the minimum value as 1. We will never get minimum value less than 1, right? We can say that the minimum value will be 1 or maybe something bigger than 1. It cannot be less than 1. This is the smallest possible distance that will be there. What will be the biggest possible distance between any two cows? The biggest possible distance will be if we place the first cow at first stall and the second cow at the last stall, right? That will be the biggest possible distance. So I would say max distance is going to be stall at n minus 1 minus stall at 0. This particular difference value is going to be the maximum distance that you can get between any two cows. For example, here the minimum distance that can exist between any two cows is 1. Maximum distance that can exist between any two cows is 8. So once you have the fact that there is just 1 as the minimum value, that will be the minimum distance between any two cows, and max will be the maximum value about the distance between any two cows. Our final answer is going to lie within this range only. Can I say that? Our final answer is going to eventually lie inside this range. This is going to be our search space. This is going to be our search space. Within this search space, we need to find the optimal answer. We need to find one such distance such that all of our C cows, now not only the two cows, but all of our C cows can be accommodated in the given set of stalls, and the distance between any two cows, the minimum distance between any two cows is as big as possible. So I know my answer is going to lie within this range. I cannot have the minimum distance greater than this value or less than this value. Can I say that? Just think about it, no? Distance between any two cows can never be greater than 8, and it can never be less than 1. That's damn sure. Let's see what can be our answer. So what will I do? I will try to apply binary search here. That means I will try to divide my search space into two equal halves. I will get a value mid. I will say that let's try this mid. Let's try this mid and figure out the fact that whether we can place all of the cows such that minimum distance between any two cows is at least mid. So let's try to place the cows in the barn such that any two adjacent cows have at least mid unit of distance, right? mid unit of distance. We'll try to place the cow such that every two adjacent pair of cows have at least mid unit of distance. It can be more than mid also, but it should not be less than mid. Then we will say that mid is a possible answer. If we can place, then mid will be a possible answer, right? Mid will be a possible answer. Now, if we can place all of the cows such that distance between the two cows is at least mid, then we will definitely be able to place them with distance less than mid, right? And I want to maximize this value. I want to push it to as large as possible. Mid is a good answer, but maybe I can get something bigger than mid, right? That means try to find bigger than mid and move right. So we'll accept the right half and we will discard the left half. Otherwise, if we are not able to place all of the cows such that the minimum distance between any two cows is at least mid, we won't be able to place them with minimum distance greater than mid. So all we need to do is move left, else move left, that is discard the right half and accept the left half. Let's try here. So here we have 3 cows. The search space that you have got is 1 to 8. Okay, we got a mid. 8 plus 1, 9 by 2, 4. We got a mid 4. Now what we will do is, we will try to make sure that all of our 3 cows are placed such that between any 2 cows, the minimum distance is, or the distance is at least 4. We want to get distance at least 4. Okay, let's see. Of course, we should place our first cow in the first stall. This is a no-brainer, right? Place your first cow in the first stall. Okay. Now, we will start placing the second cow. Okay. Can I place cow C2 at stall number 2? No. Why? The distance between stall 2 and stall 1 is 1. And why we are taking these two distance? Because the last cow that we placed was at stall 1. So my stall unit minus the stall unit given for cow 1 will give me the distance between these two cows. And what is the distance between these two cows? 1. Is 1 greater than or equal to 4? No. So I can say that this distance is not at least mid. We need to do at least mid. So I cannot place C2 here. I'll move forward. Okay. Distance between C2 C1 is 3. Is this at least 4? Or is, when I say at least 4, then is 3 greater than or equal to 4? No. That means we can't place the cows here also. C2 goes to 8. Next stall. Next stall is at position 8, right? When C2 goes to position 8, what is the distance between C2 C1? 7. Is 7 greater than or equal to 4? Yes. So you have placed your second cow successfully. Time for the third cow. Now third cow will of course start from the next position, right? Now, should I place my third cow at position 9? No. Why? Because now forget about C1. The last cow that you placed was at position 8. The difference between the position is what? 1. So is 1 greater than or equal to 4? No. And you can see the stalls have ended. And this C3 cow was not able to accommodate itself anywhere. That means we were not able to place 3 cows with distance to be at least 4. If we cannot place them with distance at least 4, I won't be able to place them with distance greater than 4. I need to do high is equals to mid minus 1. And start again. This will be a new mid. 3 plus 1 by 2 is 2. Let's try to place the cows with distance to be at least 2. Okay. So first cow will of course go to the first stall. You go to C2. Can we place this cow here? No. The distance between them is 1 and we want distance to be at least 2. I move here. Can I place my cow here? Yes. The distance is 3 and we wanted the distance to be at least 2. We are good to go. We'll start with cow C3 here because the next stall is at position 8. Can we place C3 here? Yes. 8 minus 4 is 4 and I wanted the distance to be at least 2. 4 is greater than or equal to 2. I can place the cow C3 here. And you can see I have placed all the 3 cows. That means 2 is a potential answer. 2 is a potential answer. And if we are able to place the cows with distance 2, we will be able to place them in less than 2. I want to maximize the value. I want to push it towards the right. So what I'm going to do? Low is equals to mid plus 1. So now low and high both comes to 3. So low plus high by 2 is 3 again. Now I want to maintain the distance to be at least 3. Can I place C2 here? No. Can I place C2 here? Yes. I wanted the distance to be at least 3. Here the distance is 3. 4 minus 1 is 3. So 3 is greater than or equal to 3. I can place my cow C2 successfully here. No problem at all. We start with C3 here. What is the distance between C2 and C3? 4. We wanted the distance to be at least 3. Good to go. Right. And you can see I have again placed all of the cows, and 3 unit distance is a better answer, right? So I'll update my answer to be 3. And I'll try to push to the right again. So I'll do low is equals to mid plus 1. Low comes here. Now low and high have surpassed. Right. Low points to 4, high points to 3. They have surpassed. That means the algorithm ends. And 3 is your final answer. Can I say that? Right. So you can see now at last it eventually became what? Binary search on answer only. Because here the answer value is what? The distance between any 2 cows. So we figured out the search space for the answer quantity, that what can be the minimum distance between any 2 cows, and in the worst case, what can be the maximum distance. And then we start placing each and every cow manually one by one. Once you figure out the fact that you won't be able to accommodate all of the cows with at least distance mid, then you are going to break this algorithm, right? The only catch is that these stalls data should be present in sorted manner, right? If this will be shuffled in some random order, you need to sort them based on their positions, and that's it. So sorting is going to take, this is an array of length n, right? So sorting is going to take n log n time. Then you are applying binary search from 1 to max minus min. So log of max minus min. And in every binary search iteration, you are iterating this whole array again and again. This array is of length n. N log n plus n log max minus min is going to be the time complexity for this solution. And this will be very easily submitted. All you have to do is just sort the array, apply binary search with each possible value of mid, try to check whether you will be able to place all of the cows with the distance to be at least mid. That's it. This is going to be the corresponding solution for the problem aggressive cows. So let's try to write a pseudocode so that we can understand how can we implement the question. We'll first of all have a function can place cows. Can we place the cows in the based on the given stalls array? N is the length of the stalls array, C is the total number of cows, and mid is the distance that we are going to maintain, at least distance that we are going to maintain between each cow. I will say that let's prepare a count to be equal to 1. Okay. And we will say last position is equals to stalls as 0. What I'm doing here is that I know that at least one cow so we can always place. So count should be, this is the count of cows. So we know that one cow will definitely go, no problem. And we should technically place our first cow on 0th index or the first stall only, right? We can place one cow definitely. We can place first cow on first stall. Okay. Now the first cow is placed at the 0th stall, and now we need to start the movement. So what I'm going to do, I'm going to iterate over the stalls. So on the 0th stall, so we already have the 0th cow. Now let's move to the rest of the stalls. I'm going to check if stalls at I minus last position, if this value is greater than or equal to mid. So what's happening here? I'll say that if the position of the current stall minus the last position where the last cow has been placed, we subtract this so that we can get the distance between if we place the current cow at ith position and the last cow. If this distance between the two adjacent cows is at least mid, then we can place this cow here. How do you place the cow? I will do count plus plus so that you have placed the second cow, third cow, whatever it is, right? And then we update the last position, because now once you have added the new cow, now with respect to this new cow, the rest of the cows are going to do the distancing. For example, when we used to place C2, we used to check it with C1. The moment we place C2 properly, now for C3 you are going to check with C2. If there is one more cow, then for that C4 cow you are going to check with C3. So you have to always check with respect to your last position. So you need to update your last position, that I'm going to put my new cow at stalls at I. So my last position becomes stalls at I. Right. And then we are going to check one more thing, that if count becomes, let's say, greater than or equal to cows, then we return true. That is, I wanted to place, let's say, C cows. This should be C. I wanted to place C cows and I am able to place C cows. There are few stalls still left, but no problem. We are able to place all the C cows. That's what our achievement was. We'll just return true. Otherwise, at last, we'll return false. If at any point of time we were not able to place all the cows, then the count will remain less than cows and we won't be able to place them. That's going to be your function using which you can check whether you can place the cows in the stalls or not. Right. If you have to write the binary search part, low is equals to 1, high is equals to max minus min, while low is less than or equal to high, mid is equals to low plus high minus low by 2, right? And then we say that if can place cows in the given stalls array N, C and the mid. If we can place the cows, then we'll say that we found one potential answer, but we can found something better on the right side of it. Else I is equals to mid minus 1. And that's it. Using this basic while loop, you can compute your answer and finally you just return answer here. That's it. This is going to be the simple solution that you can build for the aggressive cows problem in whatever language you are coding. Also, if you are somebody who is actually willing to prepare for software engineering interviews and want a more structured curriculum around high-level design, low-level design, other aspects of interview preparation around system design, or you are more interested in around learning back-end development concepts with Node.js, Spring Boot and whatnot, then do check out the website of algocamp.io. Here we have tons and tons of live courses where we talk about some really interesting concepts around software engineering. So do check out the website and start preparing for your software engineering career, because all of the concepts that we are going to talk about are one of the most important ones to become a better engineer and also to actually crack all the software engineering interviews. So let's come back to the video.
Hi everyone, hello, welcome to the next video, where in this one we are going to solve a new problem, that is book allocation problem. Okay, now we are going to solve a bunch of binary search problems which are based on the concept of minimax, right? So let's first read what this problem statement says and then we'll figure out a optimized way to solve this. So the question says that you're actually given n books and along with that you're also given m students. Now over here you are given the number of pages in each and every book also in ascending order. Okay, so the ordering over here is ascending. Now, the task is to assign books in such a way that the maximum number of pages assigned to a student is minimum, right? A very typical way to identify whether it's a minimax question or not, right? The maximum number of pages assigned to a student is minimum. okay, with the condition that every student is assigned to read only some consecutive books, okay, and then you have to print the minimum number of pages. So for example, if over here the value of n is equal to 4 and the number of pages are 12, 34, 67, 90, the number of students are 2. So there are 4 books that is to be read by 2 students, okay. So in this case the output is there are 2 students, so these are the following combinations of how we could really do the allocation, okay. First is the first student will only read 12 book with the 12 pages, and the other student will read the book with the pages 34, 67 and 90. Okay, now over here the maximum number of pages allocated is to the student 2, and what are the number of pages? 191. In the other situation, let's say another possibility is 12 and 32 of 34 is read by one student and 64 and 90 is read by another student. Now in this case, the maximum number of pages is allocated to the student 2 with 67 plus 90, the value is 157. Okay, so this is the first part. The maximum number of pages allocated to a student. Okay, in every combination, what is the maximum number of pages allocated to a student? Now over here, next we have a combination where the student 1 takes up 12, 34 and 67. The other student takes 90. In this cases, the maximum number of pages allocated to any student is 1, right? Which is the maximum number of pages allocated to a student is 1. And what is the value? 113. Okay. Now of all the 3 cases, option 3 has the minimum number of pages. Okay. Because you will see in the first particular option we have 191 as the maximum pages, in the other one we have 157, and in the third one we have 113. And we always want to minimize the maximum number of pages allocated to a student. So in this case the answer is 113. Okay, so this problem is what is a very typical binary search problem that we are going to solve. All right. Now, moving on to figure out an optimized way to do this, always remember that whatever question you have on binary search, the basic constraints should be followed. First, you should have a search space, right? And that search space should be monotonic in nature. It should follow a certain kind of ordering, right? Over here. So once you know, once you have identified the search space for the answer, right, and you always know that the answer is going to lie in that range, then you can apply binary search over it, right? How do you apply binary search? You find the middle value after identifying the search space, right, and post that you basically take a decision based on the middle value, right? And if the middle value is good, if the middle value is something that would lead to a favorable answer, it becomes a candidate for answer, and the better answer is looked on the left side. Okay, because why left side? Because here we have to minimize. Okay, so let's first move step by step. Okay, and then try to pretty much solve this question. Okay, now first let's try to identify the search space. Okay, in this we have 12, 34, 67, 90. We have 12, 34, 67 and 90 over here. Okay, now in this case, what could be the maximum range possible over here, right? The maximum could simply be that all the books are to be read by a single student. Okay, if all the books are to be read by a single student over here, that will lead to the highest possible value of the answer over here. So in this case, what will happen is, when you will do the summation, you will have 12, 24, 67 plus 90 over here. What are you going to get when you add all of them? (203), right? This is going to be the maximum possible answer of the range. Okay, Now we have to see the minimum possible answer or the minimum possible value. Don't you think if you are given n books and you also have parallelly, let's say n students only, m student where n is equal to m, okay? In this case, every student will basically will be reading one book, okay? And the answer will be the maximum value of the array. Okay, that means the student which will have to read the maximum amount of pages is going to be defining the answer as well. Okay, so in this case, the maximum value is 90. So we can say for sure that the answer would lie in this range. Okay, so now we know that this is going to be the range of my answer. Okay, and somewhere my final answer lies over here. Okay, and what does this search space represent? The search space represents the maximum number of pages read by a student. Okay, this represents the maximum number of pages read by a student. We'll find a middle value over here, right? And then we'll take this forward. First, let's try to implement this much what we have written so far, and then let's try to then understand the logic of how the concept of mid would work. So over here, we would be taking certain values of input. Let's say we have S out, and minimum pages is what we are going to pass in. New int as one parameter we'll pass 12, 34, 67, 90, comma 2. That means it needs to be divided among 2 students. Now over here, this is going to be my value m, which is the number of student I have, and this is the array. Okay, first let's try to define the range over here. Let's say the summation value could be very big, so, or let's make it simple only for now because the idea is to understand the concept, right? And int maximum value of the, we can start with 0 only, the maximum value, because we are not going to have book with negative pages. For int I is equal to 0, I is less than arr dot length I plus plus. Okay, so sum is equal to, whenever you are trying to find the sum, you'll simply be adding the values of the array. And for finding out the max is going to be math dot max of the max value so far and the arr of I value you have. Okay, this is going to be returning int as a function. We can simply check as well over here if we do have the right values or not in these 2 variables. So over here, when I run this, so you can see 90 and 203 are the 2 values which I require as well. Okay, now that you have it, you have your search space. Int low is equal to max, int high is equal to sum. Okay, now we'll try to apply the concept of binary search. There is going to be a final answer which we will return in the end. And now while what low is less than equal to high, what we are going to do is first we are going to find the middle values, which is low plus high by 2. Okay, now see what happens over here is what we have discussed till now. Now what will happen is you basically find out the middle value over here. Okay, what does mid represents? Mid represents the maximum number of pages read by a student. Okay, and if somehow I am able to let's say when I try to find the mid over here, which is 90 plus 203 by 2, it will be something of this sorts. Okay, this approximately, let's say I take 300 by 2, so it will somehow come as 147 something. Okay, so this is my, let's say, middle value. Okay, now what I'm trying to say over here is, let's say the middle value is 147. That means the maximum number of pages read by a student is 147. Okay, so now what I will do is I will try to see, based on the books given to me so far, can I actually do a division in which no student is actually reading more than 147 pages. Okay, I'm repeating myself once again. What we will actually do is, since the middle value is 147, I will see, can I divide the given books among m number of students in such a way that no student actually reads more than 147 pages. Okay, and if that is possible, that means this is a good candidate to actually become an answer. But where will the better answer lie? On the left side. Why did I say left side? Because on the very left side, what I will see is a more minimized value. Okay, it's like saying, if us, or if that bifurcation can be done in such a way that all the students are reading a maximum of 147 pages, that means we should try to go even lower, right? Even maybe a lower value would also satisfy the case. Okay, but for example, I choose a case, for example, the value is 110, right? And there is no division possible in which all the students are only reading, let's say, not more than 110 pages. That means we need to increase the maximum value. Okay, so there will be a good function which will check if the current good value, or the current mid value is good enough or not. Okay, and if it is, that means this is definitely a candidate for answer, but a better candidate answer is what we will look on the left side. So how do you move to the left side? You do high is equal to mid minus 1. Else, because the value is not sufficed, what you will do is you will move towards the right side. So you will do low is equal to mid plus 1, and in the end you will simply return the answer. Okay, now let's see how are we going to do the part to check if a particular mid value is good or not. What were the number of pages we had? 12, 34, 67, 90. Okay, so now we have to see, if I keep the maximum value as 147, can I do the allocation in such a way that k students, right? K students, k or less than k students are able to read all the books. Okay, so what I will do is I will initially start with the number of students that is first reading the book is 1. Okay, and the sum of the pages that it has read so far is 0. Okay, now I will see, it is reading this book, it is fine. Then is it possible for this student only to read the next book also? Yes, because the sum of this is less than 147. Then is it possible for the same student to read this book also? It is, right? When you add all these values, right, what you will see is 103. Is it possible for this student only to read the next possible value as well? No, right? Because the moment it tries to read this book, the sum actually exceeds the given possible value. So in that case, what you will do is you will increase the number of students to 2, and this student started reading from the page 90. So the sum will be updated to 90. Okay, and since there is nothing after this, what we realized was that if I actually keep the maximum value to be 147, 2 students can actually very easily read all the books, and this maximum value or mid value was good enough for us. Okay, that means we need to move left in this case. When we move left, now basically one of the answers I have so far is 147. That is a good enough answer for me, but I need to look for the better answer. For the better answer, the high value will now here be, which is, let's say, at 146. Now you will again try to find the mid value, which is going to be 90 plus 146, which is 236 by 2. what is it, 118. Okay, so now I see if 118 as a maximum value is good enough for me. Okay, so the mid or the maximum value is 118. Now let's try to do the division among students. Let's again start with 0. So we are looking at the first student who has read 0 pages so far. Then I have the page 12. So the page 12 is over here. Okay, the student can easily read it because the maximum limit is 118. Then it tries to read the page 34. Okay, it can read the page 34, no problem at all. Then it tries to reach the page 67. Okay, it can read it because we just saw that the sum is 103, right? So over here, what we can see is that the student is able to very easily read all the pages. Okay, just check one thing. I think when I did this, I may have done a mistake over here of 7, 9, 13 and this. So it was 113, okay, not 103 in the last sum. So over here, the sum is 113 and the limit is what? 118, right? So that means this is a well enough answer. We can actually say that this student can read this many pages. Then when we try to give the same student, okay, the page book 90 also with the pages 90, that does not suffice. So what do you do is you basically break it off, upgrade the number of students and allocate this student the page 90. Okay, and now you can see 2 students, which are the total number of students we have as well, are able to read all the pages, all the books with the maximum limit 118. Okay, so that means 118 is definitely an answer, right? But we need to look for a better answer. Okay, so this was our mid, which was 118. Okay, which is a good enough answer. So what we'll do is we'll try to look for a better answer. Now how do we look for a better answer? By keeping my range like this. So this is my updated range now, 90 to 117. I'll show one more case for you. 90 plus 117 is what? 207. 207 by 2 is what? 103.5. Let's say it's 103. Okay, now what I will do is I will say my mid is 103. I need to again do the bifurcation amongst the students in such a way that all the students are basically reading no more than 103 pages. Okay, let's start again. Now the first student I have and it has read so far 0 pages. Can I allocate the page 12 to book with the 12 pages to it? Yes. Can I do with 34? Yes. Okay. Now can I do with 67? No. Right? I cannot make the student 1 read the book also with 67 pages because the maximum page count is 103. Okay, so in this case it does not satisfy the situation. That means I need to upgrade the number of student to 2, right? And the sum for it is going to be 67. Now that student, can it read the book with 90 pages also? No, because it will exceed the sum. So I will have to increase the number of student and that will read the page 90. Okay, so although we are still able to read all the pages over here, but you will see the number of students value has increased, right? We actually have only 2 students, right? But here 3 students were actually required to read all the books if I keep the maximum limit as 103, right? So this maximum limit is not sufficed, right? I cannot add another student. I have only 2 students and I need to do the division among those 2 students only in order for them to be able to read all the pages. Okay, so in that case, what I can say is the mid value I just found, which was 103, is actually not good enough. So in that case, what do? You increase your low value only moving forward. So this is now my updated range from 104 to 117. Okay, and I think you get the gist what is happening over here, right? Whenever I keep the max mid value too low, what will happen is the bifurcation will not be possible and the students will not be able to read all the pages with the required number of students we have, right? More students will be required. Okay, so in that case we increase the value, but if the value is enough, we try to kind of come closer to the actual answer by minimizing it. So it's very simple now. What you could do over here is this function will return Boolean value, and we have to make sure that each student reads at most mid number of pages. Whenever the value exceeds, we basically allocate the book to another student. The student required is what? First student we are dealing with, and the sum so far of the pages it has read is 0. Now go to each and every element. I do I plus plus. If the value ARR of I is greater than mid, in the good function I should pass the array also, and k as well. Right? If this is good enough, what we could simply say is if ARR of I is greater than mid, in that case we return false. Okay, what does that situation means is, let's say you basically kept the limit to be 103, okay, and there was a book which was having 150 pages. You can easily see, right, this is not sufficing our test cases, correct? There is no point of even iterating over the rest of the array. The moment you come across a single book only which has more pages than the at most pages I allocated, that means there is no point of looking at the answer. Although this case might not ever come if you are keeping the low limit as the max value of the array. Some people keep the low limit as 0. So in that cases, we may come across this situation. So always it's good to be safe. Now we check if the sum the sum I have so far, right, when I add the next book pages to it, if it exceeds the mid value, right, I am already having the number of pages that is read by the student 1. Okay, if I add another book to that student and if it exceeds the mid value, what did we used to do in that? First of all, we need to increase the number of students because the next student is going to read it. Also, the sum will be updated to that part. Okay, that is what we did over here, right? 12 plus 34 was read by a single student. So the sum was different, right? In that case, it was 46. But the moment 67 comes, what we will do is we will update the student required also. Now the student required will be true and the sum of the pages read by that student is going to be 67. Okay, remember this variable maintains the actual number of pages read by that particular student. Okay, so we are basically going to update it. It may happen that when you actually do this updation, right, we just saw that sometimes the students are able to read all the books, but we require more students. So if you come across this situation that the student required becomes actually greater than k, which is the number of students you have, then also you return false. Okay, otherwise what do you do? Otherwise, if let's say the sum is actually not greater than mid, so for the current student, just keep adding that page. Okay, and in the end, if you never actually return the false from this loop, that means you will return a true. Okay, if you would have ever exceeded the number of students, you would have returned a false. If you never returned a false, that means you could return a true in this case. Okay, and this is going to be our final implementation for this. This is going to be M. Okay, and you can see the final answer is 113. I can delete this. We don't require this anymore. And you can see the final answer is 113, which pretty much is the final answer as well. Okay, just to quickly reiterate, what we do in binary search and specifically minimax problems is we try to find out the search space, right? The search space in this was the maximum element of the array because one student will obviously read at least one book, right? And the maximum pages that it could read would be maximum element of the array. And then we could have the sum of all the elements of the array. For example, if there were n books and only one student. Okay, and then once we identify the search space, we find the middle value. The mid basically represents the maximum number of pages that is read by a student. Okay, and if I am able to basically put a limit on the number of pages that is read by a student, and if all the case students are actually able to follow that as well, okay, all the case students are able to follow that and don't read more than mid number of pages, then we are actually good to go. That particular mid value is a good candidate to become an answer. But since the question says not to find any answer but to minimize the answer as much as possible, that is why what we do is we actually move towards the left to even look for a smaller value. Okay, but in another situation, what would happen is sometimes the mid value is actually too small, right? That means K students are not basically able to read all the pages if the limit is so small. In that case, you need to increase the value of mid. How do you do that? By moving towards the right. Okay. So this is a typical, very good binary search question. Again, very, very popularly asked in interviews. Here you are basically applying a complexity of log of n for the concept of binary search. And in that you are basically kind of checking the good function. The good function has a complexity of O of n. So the overall complexity for the solution for this problem becomes O of log n, O of big O of n log. Okay, and this forms our answer for the question book allocation problem. I hope this is clear to all of you. Thank you.
So if you want to code the solution of capacity to ship packages in Java, right, what I'm going to do is, you can see I'm getting the total weights and the maximum weight so that I can set the limits of low and high. Within the bounds of low and high, I'm going to make the binary search work. So you can see here I'm going to put mid to apply binary search. And there is a function that I have written, can ship with mid weights within D days. Okay. This function is going to tell you that with the mid capacity, will you be able to deliver the packages within D days or not? Okay. If you are, then this is a candidate answer for us, and we will try to find even less capacity. If you cannot, then we have to increase the capacity. And how do you find out whether you can deliver it or not? You try to calculate the total weight one by one. If the total weight plus the weight of the next item is greater than the mid value that we have considered, then that means you have to increment days. That means you need one more day to get the value done, and you reset your total weight. Otherwise, you keep on just adding the weights. You keep on adding the weights. At last, to consider the last set of weights, because for them days count never incremented, you have to increment that as well. So once day count you are going to increment for the last set of days, and then you are going to check whether the days count that we require is less than or equal to D or not. If it is, then you can ship. If it is not, then you cannot. Now, to just tell you why you are doing days count plus here, let me show you. So let's say you keep total weight is equals to 0, days count is equals to 0. Now we are going to start from here. I is here. Okay, we will say, is total weight plus the weight at I greater than mid? No. So I will add it. So total weight is 1. We go ahead. Is 1 plus 2 greater than mid? No. So I will add it. This becomes 3. Is 3 plus 3 greater than 15? No. I will add it. This becomes 6. Is 6 plus 4 greater than 15? No. I will add it. Becomes 10. Is 10 plus 15 greater than 15? No. I will add it. This becomes 15. Is 15 plus 6 greater than 15? Yes. That means the previous set of items can be incorporated in one day. So I will increment days count to 1. And I will reset TW to 0 because now you have to consider a new day. From here, a new day starts. Okay. So 0 plus 6 is greater than 15? No. So I'll add it. 6 plus 7 greater than 15? No. I'll add it. Is 13 plus 8? Is 13 plus 8 greater than 15? Yes. So what does that mean? The previous set of elements needs their own one day. So I'll increment the days count and I'll reset TW to 0. I'll reset TW to 0. Okay. Cool. Now 0 plus 8, 8. 0 plus 8, 8. Is, and then we move ahead. Is 8 plus 9 greater than 15? Yes. That means it needs its own day. So day equals to 3 and we reset TW to 0. Now 0 plus 9 is 9 and we move ahead. We say 9 plus 10 is greater than 15. Yes. So what do? You increment the day and you reset TW to 0. Then
0 plus 10, 0 plus 10, 10, and that's it. And that's it. You ended the loop. Can I say for the last element, you never checked that whether you need a day for the last element or not, because you need 1 day for this, 1 day for this, 1 day for this, 1 day for this. But we didn't consider the 1 day for the last element. That is why we are separately doing days count plus plus here, right? And then eventually when you get the total days count that you need with mid capacity of the ship, if the days count is less than equal to d, that is the amount of days that have been allocated to us. If it is within the bounds, we can ship. That's it. So we can try to submit the solution. You can see the solution works absolutely fine. Okay. And what is the time complexity of the solution? You can see this is the loop of binary search. The binary search loop, is going from maximum to the sum of weights. Okay. And in each binary search loop, you are calling this function, which is nothing but an order of n loop. Okay. So what is the bound of binary search? From maximum to sum of weights, it is log of sum minus maximum. And we can say when will be this value the biggest? When the maximum is, like, if all of the elements are same, 1 1 1 1 1 1 1, maximum is also 1, but the sum is going to be high, right? So in that case, this value will be equivalent to log of the sum of the weights. And for each binary search call, you have an order of n loop. So the time complexity becomes order of n log of sum of weights. This will be the time complexity. And the space complexity will be order of 1, because we are not taking any extra space altogether. That's the complexity analysis for the corresponding solution. So this is a new question coming from lead code, problem number 1011, capacity to ship packages within D days. A conveyor belt has packages that must be shipped from one port to another within the given number of days. So there is a conveyor belt which has some packages on the top of it. And these packages are expected to be shipped from one location to another location, right? The ith package on the conveyor belt has a weights of I. Each day, we load the ship with packages on the conveyor belt in the order given by the weights. Okay. So what is there? For every particular package, we have the weight of the package. And what do we do? One by one, we actually load these packages on the ship. We may not load more weight than the maximum weight capacity of the ship. So there is a maximum capacity of the ship, that is how much amount of weight the ship can actually bear, right? That's a maximum capacity that for the ship that is already available. Okay. Or technically this is the one that you have to find, but like just assume that this is, let's say, given to you. So if this capacity is given to you, then what you have to make sure that you cannot load more weight than the maximum capacity of the ship. Just think about it. If the maximum capacity of the ship is 100 ton, or I would say, let's say 100 kg, okay, and you try to put on packages of 150 kg weights, then it won't be able to bear it, right? You can maximum put packages with the cumulative sum of the weight as 100 kg. Now what you have to do is you have to return the least weight capacity, that is the minimum capacity you have to return of the ship that will result in a packages on the conveyor belt being shipped within D days. So what you have to do is you have to return the minimum capacity of the ship that will result in all packages on the conveyor belt being shipped within D days. Okay. For example, if this is the set of weights of the packages given to you and there are 5 days, then bare minimum the weight of the ship should be 15 in order to make sure that all of these packages are going to be delivered within 5 days, right? If you see the constraints, then weights array length can be as big as 5 into 10 is per 4. Each individual weight can be as big as 500, and the number of days can also be as big as 5 into 10 is per 4. This is the problem in hand for us. Okay. So what the question exactly says that, like, let me just quickly do one thing. Note down the test case. 1 2 3 4 5 6 7 8, 9, 10, and number of days is equals to 5. Okay, cool. So you can see this is the packages. Now an interesting part is that the order of these packages is important. Order of the packages is important. Why order of the packages is important? Because in the question it is written that you have to load these packages in the same order that they have been given to you. For example, the package with weight 1 has been given to you first, so this needs to be loaded to the ship first. Then package with the weight 2 is given, then this needs to be loaded after 1 and before 3, and so on. So this order needs to be actually recognized. Now what you have to do is you have to find the minimum capacity. Okay, the question asks us to find the minimum capacity of the ship. Now if I try to define capacity of a ship, you can say capacity of the ship is the maximum weight the ship can carry. Right? Capacity means the maximum weight ship can carry. Right? So if you have to find the minimum capacity, then technically what you have to do is you have to minimize the maximum weight ship can carry. Right? Very easily I can interpret it like this, that if you are there for asking you to find minimum capacity, and capacity means the maximum weight the ship can carry at a point, then you have to minimize the maximum weight of the ship. Whenever you have a case of minimize the maximum or maximize the minimum, these kind of scenarios, always and always try with binary search. Okay, cool. Now just think about it. If there is a ship and there is a start point and there is an end point, in one, I would say, round trip, the ship gets loaded with a bunch of packages, takes this from the start point to the end point, and then comes back on the same day. Right? So the whole to and fro journey is completed in one day. And what do you have to do is you have to figure out that what should be the minimum weight of the ship that you are able to deliver all the packages within D days. Within D days means in less than or equal to D days. Right? So just think about it. Let's say if these are the weights of the packages, and let's say we say that can the minimum capacity be 5 kg? Right? Think about it. Let's say we try to figure out whether the minimum capacity be 5 kg or not. Let's think about it. If the minimum capacity is 5 kg, then in the first day you can only send these two packages. Why? Because the moment you add 3, the weight of the ship will be more than 5. So on the first day you send this, on the second day you send this, third day you send this, fourth day you send this, and now the remaining weights you cannot even send. The remaining weights you cannot even send. Can I say that? Because weight of the ship you assumed as 5, and there is a package of weight 10 kg. This 10 kg weight can now not be loaded. Right? This is the problem. So can I say the bare minimum capacity should be maximum of the weights? Can I say that? Like bare minimum we should keep at least 10 kg. Bare minimum we should at least keep 10 kg, so that at least even in a single day only, but we are able to get the maximum load also. So if the weight is 10 kg, let's see what happens in that case. In 10 kg in day 1, you can send these 4 packages. 4, 5, 6, 7, 8, 9, 10. So all of these can come. In day 2, you can send 5. Day 3, you can send 6. Day 4, day 5, day 6, day 7. So if there is 10 kg, you need 7 days to actually ship all of the packages. Right? Now, you can see the total number of days available was only 5. So this capacity is too less. We need to increase the capacity. For example, let's say you say 15. You say 15. Now, if let's say you have 15 kg, in 15 kg, you can actually send these 5 packages on day 1. these 2 packages on day 2, day 3, day 4, day 5. So can you see in 15 kg weight, you can actually send it in 5 days, right? So that's what I want to actually tell you, that what you can do is you can reduce it in a searching problem. Reduce it to a BS problem. How? You have to define a search space. We can say that our answer will be lying in the range of, I would say, maximum weight, right? Our minimum because what do you have to find? We have to find minimum capacity. Capacity is a unit of weight. So our answer will also be in the units of weight, right? So bare minimum, our answer should be maximum weight. And just think about it. If you have to make it go the fastest, like if you want to deliver this package, all of these packages in the fastest possible manner, how can you deliver it? You can deliver it in 1 day. If you want to deliver it the fastest way, you can deliver it in the one way where you just take 1 day and take all of them together. If you have to take all of them together, the capacity of the ship should be sum of all of the elements. Think about it. If let's say I say deliver all of these packages in your ship in 1 day. If you have to deliver it in 1 day, then what do you have to do is you have to take all of them at one point of time. If you have to take all of them at one point of time, your ship should be able to bear the load of all of them together. What is the load of all of them together? Sum of the weights of this. So you can say the maximum weight you need in your search space is the sum of the weights. Can I say that? And then your answer is going to lie inside this range. Within this range, I'm going to divide this range into 2 halves. Mid. I'll get a probable weight. Now there will be 2 choices. What is this mid going to represent? Mid is the capacity we are trying for the ship. Okay. Now there will be 2 cases. Either you can use the mid amount of capacity and you cannot deliver within D days, or you can deliver within D days. Okay. Or you can deliver within D days. Okay. There will be 2 choices. Either you will be able to deliver it within D days, or you will not be able to deliver it within D days. If you are not able to deliver within D days, right, keeping mid as the capacity, then with a lower capacity also you will not be able to deliver it, right? Because lower the capacity of the ship, higher the number of days. Think about it. Lower the capacity of ship, lower will be the number of packages that can be loaded, higher will be the number of days required. So if you cannot deliver it in mid number of days, if you cannot deliver it with mid weight, then you will not be able to deliver it in less than mid weight. So you go right. You go right and increase weight or increase capacity. If you can deliver it in mid weight within D number of days, then mid can be a probable answer. Mid can be an answer. And if you are able to deliver it with mid capacity, you will definitely be able to deliver it within D days in more than mid capacity. So no need to go on the right, you go left. You go left and decrease the capacity. Right? Think about it. If it is feasible to actually use this mid capacity and deliver it within D days, so of course with more capacity of the ship, you can deliver it within D days, but you want to minimize this capacity, right? You want to find the minimum capacity, so you go left. And now, just think about it. How can you figure out whether the given mid is a feasible capacity to deliver within D days or not? What you can do is, you take mid, you got a mid, you just iterate on this array because they have mentioned that the order matters. You start iterating on this array. You start taking sum. For example, mid is equals to 15. You start taking sum of the elements. The moment the sum becomes equals to 15 or greater than 15, you break it as day 1. Then again you start taking sum. You break it as day 2, day 3, day 4, day 5. You can keep a days count, right? You can keep a days count initially equal to 0. The moment the sum of the parcel becomes equal to 15, right, you're going to break it. Then you're going to break it. Then break it. At every break, you increment the days count. If the total days count is less than or equal to D, if the total days count is less than equal to D, then this is a feasible weight. We can go ahead. Otherwise, it is not a feasible weight. That's it. That's how you can actually try to solve this problem. So now what do we have to do is, first of all, if you want to code this solution, you need to get the bounds. To get the bounds, we need total weights initially equal to 0 and max weight initially equals to, let's say, -1. Okay. And we'll say for I equals to 0, I less than weights, I plus plus. Okay. We will say total weights plus equals to weights at I, and maximum weight is equals to maximum of, sorry, math dot max of max weight comma weights at I. Okay, cool. Now let's set the lower bound and upper bound. So, or I would say lower limit and upper limit. So lower limit will be max weight and higher limit will be total weights. I'll say while low is less than or equal to high, we'll calculate the mid. Same template or again and again coming up. Low plus math dot floor of high minus low by 2. Right. And then we are going to write a function can ship with mid weight within D days. Okay. So we'll write a function can ship with mid weight within D days or not. So I'll say weights, I'll pass mid, I'll say D. Okay. And we will say that if we can ship within D days, mid D, if we can ship, then we'll try to find something even lesser. So I'll say let answer is equals to, let's say initially equal to high, and I'll say we'll reduce it. So I'll say answer is equals to mid, and then we want to reduce it, so we go left, high is equals to mid minus 1. Else low is equals to mid plus 1. Okay. And now here let days count initially equals to 0. Right. Days count initially equals to 0. Right. And then what we will say is, we'll say for let I equals to 0, I less than weights, I plus plus. If at any point of time, if at any point of time, and let's also keep let TW as total weights. Okay. If we'll say TW total weight plus weight of the current parcel becomes greater than mid, then what do? We will increment the days count and we will restart TW to 0. Just think about it. Just think about it like this. So let's say you have a TW equals to 0. You go here, you add it to 1. You go here, plus 2 is 3. You go here, 3 plus 3 is 6. You go here, 6 plus 4 is 10. You go here, 10 plus 5 is 15. You go here and you check. Is 15 plus 6 greater than mid? Yes. If 16 plus mid is greater than 15 plus 6 is greater than mid, then you increment the days count to 1. That means these many packages will go to day 1 and you reset TW to be equal to 0, because from here you have to reset your limits. Okay, from here you have to reset your limits. That is what we are going to do, and eventually we'll say TW plus equals to weights at I. Right, TW plus equals to weights at I. I believe this should be good. And yeah, at last what we are going to return is, we are going to return if the days count required is less than equal to D or not. If it is, then you can deliver it within D days, and that's it. I'll return answer here. Okay, this looks good. This looks good. Let's try it out. 1 second. Okay, this should be days. This here should be days because the variable name is days. See, variable name in the function is days. Okay, cool. Okay, so we are getting -1. Let's see why is that. Um, Total weights is this, and maximum weight. One second. Oh, my bad. This should be weights dot length. This also should be weights dot length. Okay. This for loop should go till weights dot length, not less than weights. Okay, cool. Now we are not getting -1. Let's see what we are getting. We are getting 11. Okay, so probably we are not converging it. So let's see how things are coming up. So every call, I'll say console.log mid comma days count. Let's see for a particular value what is coming up. So we tried 32, we tried 20, we tried 14. Okay, with 14 it said 5 days. Okay, with 14 it came as 5 days. There is some problem, I believe. So if you can ship within 5 days, right? One second. So there is a small issue with our code. What is the issue? So the thing is that the last set of days is not being included. Last set of days is not being included because what we are doing is, for example, let's say this gave you day 1, this gave you day 2, day 3, day 4. Then after day 4, you reset TW equals to 0. You add this weight and that's it. You never incorporate days count value for the last one, right? So what you should do is, at last you should say days count plus plus for incorporating the last day as well. So this is what we are missing. Let's run the code now. And you can see 15 is coming up. This looks good. Let's try with another test case. One second. Ta-da. Sorry. Here we go. Let's try to submit. And that's it. That's how you can actually solve the problem of container delivery. So this is a new question coming from LeetCode problem number 2616. The question says that you are given a 0 indexed integer array nums, right? So there is a 0 based indexing integer array nums and an integer value p. So you are given two things, an array and an integer value. Find p pairs of indices. Indices means the indexes. So you have to find pair of indexes, p pairs of indexes of nums of the given array such that maximum difference among all the pairs is minimized. So whatever type of pairs you try to figure out, you can calculate the difference between the pairs. Whatever is the maximum difference between any pair, that value should be as less as possible. Also ensure that no index appear more than once in the pair. So you can only use one index in one pair. Note that for a pair of elements I and j, the difference of the pair is absolute value of the difference. So it's not like you have to just take nums at I minus nums at j. No, you have to take the absolute value also. Absolute value means if the difference comes as -5, then the absolute value of -5 is 5. If the difference comes as 7, absolute value of 7 is 7. So the negative will become technically positive. Return the minimum maximum difference among all p pairs. We define the maximum of an empty set to be 0. Okay. So for example, this is the array p is equals to 2. You have to find two pairs. You have to find two pairs such that that difference between the maximum difference between any pair is as less as possible. Now just think about it. The first pair is formed from the indexes 1 and 4. So 1 and 4. And the second pair is formed from the indices 2 and 5. So 2 and 5. And can you see? The first pair is giving you a difference 0. Second pair is giving you a difference 1. So here, the max difference is what? 1. And hence you have minimized. If you have taken any other pair, if you would have taken any other pair, for example, you would have taken 10, 7. then the difference would have been 3. This value would have increased. Same thing here. 4 to 1 2. You need just one pair. If you one pair, then what maybe you can do is you can form a pair with 2 comma 2. Right, this 2 and this 2. So the difference is going to be what? 0. You can never have a difference lesser than 0 because it's an absolute value. The length of the array can be as big as 10 is per 5. Elements can be as big as 10 is per 9. And the value of p will be half of the array length. If you see, it's a medium mark problem, 2200 upvotes. And previously this has been asked in Amazon, Apple, Microsoft multiple times. So it's a fairly interesting question, I would say. So this is a new question coming from lead code problem number 2616. The question says that you are given a 0 indexed integer array nums, right? So there is a 0 based indexing, integer array nums, and an integer value p. So you are given two things, an array and an integer value. Find p pairs of indices. Indices means the indexes. You have to find pair of indexes, p pairs of indexes of nums of the given array such that maximum difference among all the pairs is minimized. So whatever type of pairs you try to figure out, you can calculate the difference between the pairs. Whatever is the maximum difference between any pair, that value should be as less as possible. Also ensure that no index appear more than once in the pair. So you can only use one index in one pair. Note that for a pair of elements I and j, the difference of the pair is absolute value of the difference. So it's not like you have to just take nums at I minus nums at j. No, you have to take the absolute value also. Absolute value means if the difference comes as minus 5, then the absolute value of minus 5 is 5. If the difference comes as 7, absolute value of 7 is 7. So the negative will become technically positive. Return the minimum maximum difference among all p pairs. We define the maximum of an empty set to be 0. Okay. So for example, this is the array p is equals to 2. You have to find two pairs. You have to find two pairs such that that difference between the maximum difference between any pair is as less as possible. Now just think about it. The first pair is formed from the indexes 1 and 4. So 1 and 4. And the second pair is formed from the indices 2 and 5. So 2 and 5. And can you see? The first pair is giving a difference 0. Second pair is giving a difference 1. So here the max difference is what? 1. And hence you have minimized. If you have taken any other pair, if you would have taken any other pair, for example, you would have taken 10, 7, then the difference would have been 3. This value would have increased. Same thing here. 4 to 1 2. You need just one pair. If you one pair, then what maybe you can do is you can form a pair with 2 comma 2. Right, this 2 and this 2. So the difference is going to be what? 0. You can never have a difference lesser than 0 because it's an absolute value. The length of the array can be as big as 10 is per 5. Elements can be as big as 10 is per 9. And the value of p will be half of the array length. If you see, it's a medium mark problem, 2200 upvotes. And previously this has been asked in Amazon, Apple, Microsoft multiple times. So it's a fairly interesting question, I would say. Now in this particular question, what we are expected is we are expected to find a bunch of pairs. For example, we are expected to find p pairs. Now again, an interesting part is you have to minimize the maximum difference. Okay. The question asks you to minimize the maximum difference. Again, that same pattern of minimax, that you have to minimize the maximum or maximize the minimum. So a direct intuition that should get to your head is binary search. Okay, direct intuition that should come to your head is binary search. Now what do you have to make, what the answer range is? Answer is around the difference, and it's the absolute difference, right? You have to consider the absolute difference. How absolute difference looks like? If it is minus 7, if the difference comes as minus 7, the absolute value is 7. If the difference comes as 7, then also it is 7. That's the absolute value. Okay. Now let's just think about differences. Let's just think about with respect to differences. Can I say this difference value will be very high? It will be a very high value if there is a lot of deviation from x to y, right? If let's say x and y are too far apart, for example, x is too high, y is too low, or y is too high, x is too low. If the value is too far apart, the difference is going to be very high. Can I say that? And what we have to do is we have to minimize it. We have to minimize it. Now, what the question mean when they say minimize the maximum difference? So just think about it. If let's say P1, P2, P3, three pair comes up in one configuration, and P1, P2, P3, three pairs comes up in another configuration. Let's say this is answer configuration 1, this is answer configuration 2. Let's say P1 was 2, this is 1, this is 6, this is 3, this is 4, this is 6. Okay. Now, what is the maximum difference here? 6. And let's take it, let's say, as 5. Okay. What is the maximum difference here? 5. So, both of the configuration, which maximum difference is less? This maximum difference is less. So, this is a suitable configuration for us. So, that's what they mean when they actually ask for minimize the maximum difference. Okay. Cool. Now, if you want to get this difference as less as possible, then you don't want x and y to be too far apart. They cannot be too far apart, right? So ideally, this difference will be very less if they are very close, if x and y are pretty close. Okay. Currently, the given array that we have is arranged in random order. Just think about it. 10, 1, 2, 7, 1, 3. Okay. 10, 1, 2, 7, 1, 3. Okay. Now just think about it. How about if you sort this array? If you sort this array, you'll get 1, 1, 2, 3, 7, 10. Can I say all the elements which are close will come together? Can I say that? Just think about it. If you would have taken the difference of 10 and 1, difference would have come as 9. But if you will take the difference of 10 and 7, the difference is just 3, right? So if you will sort the array, then adjacent elements are a better candidate to make the pair rather than random elements here. If you take random elements here and you got a very high parity or very high deviation between the elements, the difference will be too high. But here, if you sort the array, then close elements will come together and close elements will decrease the corresponding difference. Can I say that? Right? So how about you sort the array? Okay. And then it's a minimax problem. So you can apply binary search. So for applying binary search, that's the first step, we sorted the array. Second step is to figure out the search space. The search space. You need to find what is the answer that you have to find. Answer is the difference. You have to minimize the maximum value of the difference. So the answer is going to be some difference. So what is the range of the difference that you can think of? The minimum difference that you will get is 0. Why? If there are two elements which are same, the difference will be 0. The absolute value can never go below 0. Can I say that? And the maximum difference you will get will be the absolute value of the maximum element minus minimum element, right? This is the maximum difference that you can make. For example, 10 and 1. This is the maximum difference that you can make. Yes or no? Right? And our ideal difference will lie inside this range. So we have defined the search space. Okay. Now, what we will do is, we will figure out a mid value. We will divide our search space into two halves and again figure out a property based on which we can take one half and reject one half. Okay. Now, let's say you got a mid. What is mid representing? Mid represents a candidate difference. And what do we have to find about this candidate difference? This candidate difference means that are we able to find at least p pairs such that the difference of the pairs is less than or equal to mid. Okay, because we are saying that mid can be that threshold value, mid can be that difference which can be our answer, right? So what we have to check? We have to minimize the max difference. So I am saying that I will try to find p pairs such that the difference among them is as big as mid. if I keep the difference of the pairs as big as mid, then can I say the maximum difference of these pairs will be what? Mid? Yes or no? Let me repeat it again. I defined my search space. The minimum of the search space, the low of the search space will be 0 because absolute value of two same values will be 0 and this can never go beyond 0 or less than 0. And what can be the maximum difference that you can achieve? Maximum difference is the difference of the maximum and the minimum element. So somewhere in between our ideal difference is going to lie. And what do we have to find? We have to find p pairs such that the maximum difference of the pair is as less as possible. So what I say is, let's assume a difference. And among this sorted array elements, I'll try to find at least p pairs. If you're not able to make p pairs, then though it's out of question. I'll try to find at least p pairs. Now, I try to find at least p pairs where the difference is less than or equal to mid, with absolute difference less than or equal to mid. Why? If you will keep the absolute difference less than or equal to mid, then let's say p was equal to 3. We found 3 pairs with absolute difference less than or equal to mid. Can I say that the maximum difference of any pair among these 3 pairs is going to be mid? So maximum difference we are able to get. And then we will try to minimize this value. So what we will do, we will take a mid and we'll take it a candidate difference. And I'll try to find p pairs such that the absolute difference is less than equal to mid. If we are able to find p pairs, now again there will be two situations that yes, you are able to find it. No, you are not able to find it. If you are able to find p pairs such that the maximum difference is mid, then you can definitely find p pairs with difference more than mid. Can I say that? You can definitely find pairs with difference more than mid. Yes or no? Can I say that? If you can find enough p pairs with the maximum difference mid, then you will be able to definitely find pairs with greater than mid, because at least 10 and 1 to will give you, right? So what we'll do, if yes, then you go to the left side. That I want to, now you find a candidate. Maybe mid is our answer, but maybe we can get a value even lesser than mid. Can I say that? We can get a value even lesser than mid because we have to minimize the maximum difference. If mid as a maximum difference is possible, let's try to minimize it. Let's try to reduce it. So we go left. And if mid is not possible, then less than mid is also not possible. So you will go to the right. You will go to the right. That's it. Now the only question comes that should come to your head is that how to figure out whether you have at least p pairs or not. That's when the adjacent element comes up. I am saying that always make the pairs in the form of adjacent elements only. Make this as one pair, make this as one pair, make this as one pair, and so on. Right? You keep on making the pairs in this particular fashion. Right? And that's how you can eventually solve this question. So for example, let's take an example here. 1, 1, 2, 3, 7, 10. 1, 1, 2, 3, 7, 10. Okay, cool. What is the low value? Low value will be 0. What is the high value? High value will be 9. We have to get a mid. Mid is 4. 9 plus 0 by 2, 4. We have to figure out, do we have at least, what is the value of p? I guess 2, right? P is 2. Do we have at least 2 pairs with the difference less than equal to 4? 1 minus 1 is 0. So we got one pair with the difference less than equal to 4. 3 minus 2, 1. We got one more pair with the difference less than equal to 4. 7 minus 10, another pair. So we have enough pairs. We have enough pairs. So if we are able to find with the difference 4 less than equal to 4, we will be able to find with greater than 4. Right? Okay. So let's try to reduce it. So I'll say high is equals to mid minus 1. High comes at 3. So 3 plus 0 by 2, again a mid value will come as 1. Okay. Do we have enough pairs with the difference less than equal to 1? And maybe also inside our answer, maybe 4 is our answer. Okay, cool. 1 minus 1, 0. So we are able to find a pair with less than equal to 1 difference. 3 minus 2 absolute value. we are able to find another pair with difference at least equal to 1, less than equal to 1, right? So we are able to find two pairs and we want at least two pairs only. So difference 1 is also achievable. So our answer becomes 1. And maybe we can find even less than this. So high comes here on 0. Now mid is also 0, high is also 0, low is also 0. Let's try to find if we have enough pairs with the difference less than equal to 0. 1 minus 1 is 0, this is good. 3 minus 2, this is not 0, right? 10 minus 7, 7 minus 3, this is not 0. So let's say 1 minus 1, 0, this is good. 2 minus 3, not possible. Then you don't jump to 7 and 10. You say 7 minus 3, not possible. Then you say 10 minus 7, not possible. So you can see 0 is not possible. 0 as a difference is not able to give you at least p pairs. Hence you are going to go to low is equals to mid plus 1. Low comes at 1 and your binary search completes. That's it. That's how you can actually solve this particular question, right? So if you want to actually code it, right? Again, let's just go step by step. We'll just go step by step. First things first, we are going to sort this array. So how do you sort an array in Java? You say arrays.sort nums. Okay. Then I store length of the array and then I initialize low as 0 and high as, what will be the value of high? It will be nums of n minus 1 minus nums of 0, because after sorting, nums of 0 is the smallest element, nums of n minus 1 is the largest element. And we say while low is less than equal to high, int mid is equals to low plus high minus low by 2, and we'll take an answer. Let's say initially equal to high, we have to minimize it. Okay, and then what we are going to do, we are going to find or write a function public boolean can form at least p pairs with mid difference, with at least mid difference. Okay, can form at least p pairs with at least mid difference. Okay, so I'll pass the nums array, I'll pass p, I'll pass mid. These are the things that you need. And then we'll say I is equals to 0 and count is equals to 0. And we'll say while I is less than nums dot length minus 1, because we have to go till the second last element only, because for the second last element, the last element can form the pair, but for the last element there is nothing else, right? Okay. And this should be at most mid, at least p pairs with at most mid difference, that is the maximum difference you need is mid. So here we should write at most. This is something that you have to keep in mind. Okay, then I will check that if nums at I plus 1 minus nums at I, okay, if this particular value is less than or equal to mid, then we'll say count plus plus, we found a pair, and we say index plus I plus equal to 2. Otherwise I'll just say I plus plus. Otherwise I will just say I plus plus. And at last we'll say return count less than or equal to p. That, not less than equal to p, greater than equal to p. That at least we are able to find p pairs. We need at least p pairs with max difference as mid. Okay, and here this check shows that whether your difference is at most mid. And then here I will say if you can form pair, if you can form a pair nums p mid, then we will try to reduce it. So I'll say answer is equals to mid, I is equals to mid minus 1, else low is equals to mid plus 1. That's it. Simple, right? Simple binary search technique and return answer. Let's try to run the code and see if it works. Okay, this sample test case works. I always recommend people to try 1 or 2 test cases at least before you submit. Run code. Yeah, looks good. And let's try to submit. And you can see, here we go. Right, here we go. We are able to submit the problem. Now, interestingly, what you will see is that while finding the difference, I'm not calculating absolute separately because it's a sorted array. If in a sorted array, you take the greater value first and the lesser values after it, it will always be positive. But of course, for your understanding, you can also do math.absolute here. But this math.absolute will be of no use because we have already sorted the array. You can see it will still come up. So this math.absolute is of technically no use. And that's how you can actually solve this particular question. Now, in this particular question, what we are expected is we are expected to find a bunch of pairs. For example, we are expected to find p pairs. Now, again, an interesting part is you have to minimize the maximum difference. Okay. The question asks you to minimize the maximum difference. Again, that same pattern of minimax that you have to minimize the maximum or maximize the minimum. So a direct intuition that should get to your head is binary search. Okay, direct intuition that should come to your head is binary search. Now what do you have to make, what the answer range is? Answer is around the difference, and it's the absolute difference, right? You have to consider the absolute difference. How absolute difference looks like? If it is -7, if the difference comes as -7, the absolute value is 7. If the difference comes as 7, then also it is 7. That's the absolute value. Okay. Now let's just think about differences. Let's just think about with respect to differences. Can I say this difference value will be very high? It will be a very high value if there is a lot of deviation from x to y, right? If let's say x and y are too far apart, for example, x is too high, y is too low, or y is too high, x is too low. If the value is too far apart, the difference is going to be very high. Can I say that? And what we have to do is we have to minimize it. We have to minimize it. Now, what the question mean when they say minimize the maximum difference? So just think about it. If let's say P1, P2, P3, 3 pair comes up in one configuration, and P1, P2, P3, 3 pairs comes up in another configuration. Let's say this is answer configuration 1, this is answer configuration 2. Let's say P1 was 2, this is 1, this is 6, this is 3, this is 4, this is 6. Okay. Now, what is the maximum difference here? 6. And let's take it, let's say, as 5. Okay. What is the maximum difference here? 5. So both of the configuration, which maximum difference is less? This maximum difference is less. So this is a suitable configuration for us. So that's what they mean when they actually ask for minimize the maximum difference. Okay, cool. Now, if you want to get this difference as less as possible, then you don't want x and y to be too far apart. They cannot be too far apart, right? So ideally, this difference will be very less if they are very close, if x and y are pretty close. Okay. Currently, the given array that we have is arranged in random order. Just think about it. 10, 1, 2, 7, 1, 3. Okay. 10, 1, 2, 7, 1, 3. Okay. Now just think about it. How about if you sort this array? If you sort this array, you'll get 1, 1, 2, 3, 7, 10. Can I say all the elements which are close will come together? Can I say that? Just think about it. If you would have taken the difference of 10 and 1, difference would have come as 9. But if you will take the difference of 10 and 7, the difference is just 3, right? So if you will sort the array, then adjacent elements are a better candidate to make the pair rather than random elements here. If you take random elements here and you got a very high parity or very high deviation between the elements, the difference will be too high. But here, if you sort the array, then close elements will come together and close elements will decrease the corresponding difference. Can I say that? Right? So how about How about you sort the array? You sort the array. Okay. And then it's a minimax problem. So you can apply binary search. So for applying binary search, that's the first step. We sorted the array. Second step is to figure out the search space. The search space. You need to find what is the answer that you have to find. Answer is the difference. You have to minimize the maximum value of the difference. So the answer is going to be some difference. So what is the range of the difference that you can think of? The minimum difference that you will get is 0. Why? If there are two elements which are same, the difference will be 0. The absolute value can never go below 0. Can I say that? And the maximum difference you will get will be the absolute value of the maximum element minus minimum element, right? This is the maximum difference that you can make. For example, 10 and 1. This is the maximum difference that you can make. Yes or no? Right? And our ideal difference will lie inside this range. So we have defined the search space. Okay. Okay. Now, what we will do is, we will figure out a mid value. We will divide our search space into two halves and again figure out a property based on which we can take one half and reject one half. Okay. Now, let's say you got a mid. What is mid representing? Mid represents a candidate difference. And what do we have to find about this candidate difference? This candidate difference means that are we able to find at least p pairs such that the difference of the pairs is less than or equal to mid. Okay, because we are saying that mid can be that threshold value, mid can be that difference which can be our answer, right? So what we have to check? We have to minimize the max difference. So I am saying that I will try to find p pairs such that the difference among them is as big as mid. If I keep the difference of the pairs as big as mid, then can I say the maximum difference of these pairs will be what? Mid? Yes or no? Let me repeat it again. I defined my search space. The minimum of the search space, the low of the search space will be 0 because absolute value of two same values will be 0 and this can never go beyond 0 or less than 0. And what can be the maximum difference that you can achieve? Maximum difference is the difference of the maximum and the minimum element. So somewhere in between our ideal difference is going to lie. And what do we have to find? We have to find p pairs such that the maximum difference of the pair is as less as possible. So what I say is, let's assume a difference. And among this sorted array elements, I'll try to find at least p pairs. If you're not able to make p pairs, then though it's out of question. I'll try to find at least p pairs. Now, I try to find at least p pairs where the difference is less than or equal to mid, with absolute difference less than or equal to mid. Why? If you will keep the absolute difference less than or equal to mid, then let's say p was equal to 3. We found 3 pairs with absolute difference less than or equal to mid. Can I say that the maximum difference of any pair among these 3 pairs is going to be mid? So maximum difference we are able to get. And then we will try to minimize this value. So what we will do, we will take a mid and we'll take it a candidate difference. And I'll try to find p pairs such that the absolute difference is less than equal to mid. If we are able to find p pairs, now again there will be two situations that yes, you are able to find it. No, you are not able to find it. If you are able to find p pairs such that the maximum difference is mid, then you can definitely find p pairs with difference more than mid. Can I say that? You can definitely find pairs with difference more than mid. Yes or no? Can I say that? If you can find enough p pairs with the maximum difference mid, then you will be able to definitely find pairs with greater than mid, because at least 10 and 1 to will give you, right? So what we'll do, if yes, then you go to the left side. That I want to, now you find a candidate. Maybe mid is our answer, but maybe we can get a value even lesser than mid. Can I say that? We can get a value even lesser than mid because we have to minimize the maximum difference. If mid as a maximum difference is possible, let's try to minimize it. Let's try to reduce it. So we go left. And if mid is not possible, then less than mid is also not possible. So you will go to the right. You will go to the right. That's it. Now the only question comes that should come to your head is that how to figure out whether you have at least p pairs or not. That's when the adjacent element comes up. I am saying that always make the pairs in the form of adjacent elements only. Make this as one pair, make this as one pair, make this as one pair, and so on. Right? You keep on making the pairs in this particular fashion. Right? And that's how you can eventually solve this question. So for example, let's take an example here. 1 1 2 3 7 10. 1 1 2 3 7 10. Okay, cool. What is the low value? Low value will be 0. What is the high value? High value will be 9. We have to get a mid. Mid is 4. 9 plus 0 by 2, 4. We have to figure out, do we have at least, what is the value of p? I guess 2, right? P is 2. Do we have at least 2 pairs with the difference less than equal to 4? 1 minus 1 is 0. So we got one pair with the difference less than equal to 4. 3 minus 2, 1. We got one more pair with the difference less than equal to 4. 7 minus 10, another pair. So we have enough pairs. We have enough pairs. So if we are able to find with the difference 4 less than equal to 4, we will be able to find with greater than 4. Right? Okay. So let's try to reduce it. So I'll say high is equals to mid minus 1. High comes at 3. So 3 plus 0 by 2, again a mid value will come as 1. Okay. Do we have enough pairs with the difference less than equal to 1? And maybe also inside our answer, maybe 4 is our answer. Okay, cool. 1 minus 1, 0. So we are able to find a pair with less than equal to 1 difference. 3 minus 2, absolute value. We are able to find another pair with difference at least equal to 1, less than equal to 1. Right? So we are able to find 2 pairs and we want at least 2 pairs only. So difference 1 is also achievable. So our answer becomes 1. And maybe we can find even less than this. So high comes here on 0. Now, mid is also 0, high is also 0, low is also 0. Let's try to find if we have enough pairs with the difference less than equal to 0. 1 minus 1 is 0, this is good. 3 minus 2, this is not 0, right? 10 minus 7, 7 minus 3, this is not 0. So let's say 1 minus 1, 0, this is good. 2 minus 3, not possible. Then you don't jump to 7 and 10. You say 7 minus 3, not possible. Then you say 10 minus 7, not possible. So you can see 0 is not possible. 0 as a difference is not able to give you at least p pairs. Hence you are going to go to low is equals to mid plus 1. Low comes at 1 and your binary search completes. That's it. That's how you can actually solve this particular question, right? So if you want to actually code it, right? Again, let's just go step by step. We'll just go step by step. First things first, we are going to sort this array. So how do you sort an array in Java? You say arrays.sort nums. Okay. Then I store length of the array and then I initialize low as 0 and high as, what will be the value of high? It will be nums of n minus 1 minus nums of 0, because after sorting, nums of 0 is the smallest element, nums of n minus 1 is the largest element. And we say while low is less than equal to high, int mid is equals to low plus high minus low by 2. And we'll take an answer. Let's say initially equal to high. We have to minimize it. Okay. And then what we are going to do, we are going to find or write a function public boolean can form at least p pairs with mid difference, with at least mid difference. Okay, can form at least p pairs with at least mid difference. Okay, so I'll pass the nums array, I'll pass p, I'll pass mid. These are the things that you need. And then we'll say I is equals to 0 and count is equals to 0. And we'll say while I is less than nums dot length minus 1, because we have to go till the second last element only, because for the second last element the last element can form the pair, but for the last element there is nothing else, right? Okay. And oh sorry, this should be at most mid, at least p pairs with at most mid difference, that is the maximum difference you need is mid. So here we should write at most. This is something that you have to keep in mind. Okay, then I will check that if nums at I plus 1 minus nums at I, okay, if this particular value is less than or equal to mid, then we'll say count plus plus, we found a pair, and we say index plus sorry I plus equal to 2. Otherwise I'll just say I plus plus. Otherwise I will just say I plus plus. And at last we'll say return count less than or equal to p. That sorry, not less than equal to p, greater than equal to p. That at least we are able to find p pairs. We need at least p pairs with max difference as mid. Okay, and here this check shows that whether your difference is at most mid. And then here I will say if you can form pair, if you can form a pair nums p mid, then we will try to reduce it. So I'll say answer is equals to mid, I is equals to mid minus 1, else low is equals to mid plus 1. That's it. Simple, right? Simple binary search technique and return answer. Let's try to run the code and see if it works. Okay, this sample test case works. I always recommend people to try 1 or 2 test cases at least before you submit. Run code. Yeah, looks good. And let's try to submit. And you can see, here we go. Right, here we go. We are able to submit the problem. Now, interestingly, what you will see is that while finding the difference, I'm not calculating absolute separately because it's a sorted array. If in a sorted array, you take the greater value first and the lesser values after it, it will always be positive. But of course, for your understanding, you can also do math.absolute here. But this math.absolute will be of no use because we have already sorted the array. You can see it will still come up. So this math.absolute is of technically no use. And that's how you can actually solve this particular question. So this is a new question coming from LeetCode, problem number 410, split array largest sum. The question is a hard marked problem, 9,521 upwards. Previously asked in Google, Amazon, Adobe, Salesforce, Atlassian, PayPal, Flipkart, Apple, Baidu, PhonePe. You can see a lot of companies have been asking this question. It's a pretty famous and a hard marked problem. But till now, if you have solved all the problems that we have been discussing in mind research, this should be nothing more than easy medium to you, right? Given an integer array nums, you have been given an integer array nums and an integer k. You have been given an integer k. You have to split the nums into k non-empty subarrays. Now, what is a subarray? Subarray is a contiguous part of the array. So, if you take an array and you take a continuous cross section of the array, that's a subarray. For example, this is a subarray. This is a subarray. This whole array is a subarray. Just 7 is a subarray. 2, 5, 10, 8 is a subarray, and so on. Any continuous set of elements is a subarray. You need to split your array into k subarrays, k non-empty subarrays, such that now after splitting you can take sum, right? So such that the largest sum of any subarray is minimized. Okay. So for example, let's say you wanted to split into 2 subarrays. Now just think about it. You can make a split like 7 to 5, 10 and 8. In 7 to 5, 10, what will be the sum? It will be 15, 16, 17 and 7, 24. The largest sum is going to be what? 24, because this is 24, this is 8. Which is the largest sum? 24. But if you divide it like 7 to 5 and 10, 8, then largest sum is what? 18. If you divide it like 7 to 5, 10, 8, The largest sum is going to be what? 23. So there can be different ways to actually divide. You need to divide your array into multiple subarrays such that when you take sum of every subarray, then whatever is the maximum subarray sum, you have to choose a configuration such that the maximum subarray sum is minimized. So you can see the largest sum of the subarray is minimized. You have to return this minimized largest sum, right? You can see for 1, 2, 3, 4, 5, you can split it like 1, 2, 3 and 4, 5. So you have two subarrays, one is 1, 2, 3, another is 4, 5, and the maximum sum comes from 4, 5. If let's say you divide it in some other way, let's say 1, 2, 3, 4 and 5. If you do 1, 2, 3, 4 and 5, then the largest sum will come from 1, 2, 3, 4. That will be 10, which is higher than 9. You need to minimize this sum, and that's the question. If you see the constraints, length of the array is as big as 1000, pretty less. And each individual element is 10 raised per 6. Technically, if the length of the array would have been 10 raised per 5 also, then also you should be able to technically solve this question. Think about it. How can you solve it? Now, how can we solve this question? Now, if you want to actually solve this question, there are a few direct hints that can come up. For example, minimizing largest sum. Minimizing largest sum can be written as minimizing the maximum sum. So again, that minimax situation is coming up. Now, this situation or this question is 90 to 95% same, or maybe more than that, with the containers problem that we actually solved. Containers in D-Days. Cheat code. Right. This problem we have already solved, and it's like 99% also maybe probably exactly same. Instead of packages on a conveyor belt, you have to consider a subarray. Okay. In this particular problem, what we used to do was we used to try to figure out a day, and then we used to figure out that how many packages we can set in one day. It's very similar to that only. Now, a few people might get confused that what is the meaning of minimizing the largest sum. Just think about it. Let's say you have an array like 1, 2, 3, 4, 5, and you have k is equals to 2, and you have to make non-empty subarrays. So there are different ways to make the subarrays. One way is 1 as one subarray, 2, 3, 4, 5 as another subarray, like this. Then 1, 2 as one subarray, 3, 4, 5 as another subarray. Then 1, 2, 3 as one subarray, 4, 5 as another subarray, like this. Then 1, 2, 3, 4 as one subarray, 5 another subarray. So you can see these are 4 different configurations you have. Now what do they mean when they say that largest sum of the subarray is minimized? Now just think about it. In every configuration, let's just only consider the largest sum. Largest sum here is 14. Largest sum here is 12. Largest sum here is 9. Largest sum here is 10. So these are the largest sum of every configuration. We need to pick that configuration in which the largest sum is as minimum as possible. So you can see the largest sum which is as minimum as possible is 9. So that's why 9 is the answer. Now, because it's a minimax kind of a problem, what is the final answer that we have to figure out? We need to figure out we need to find the least max sum. Okay, so the sum is the answer. So the binary search and answer may be on the sum. Now, you have to tell me that what will be the minimum possible value of the search space and the maximum possible value of the search space. Now I can say maximum value or possible value of the search space can be the sum of the subarray or sum of the whole array. Can I say that? Because that will be the maximum sum any subarray can possess. Can I say that? So I can say the high value will be sum of array, because this is the biggest subarray and this will be the largest sum of the whole array, right? If you carefully go and see, it's all positive elements, right? It's all positive elements. That means the whole array is going to be the largest sum any subarray can possess. And according to our answer, what can be the smallest sum any subarray can possess? Like the smallest sum also will be what? The largest value. Think about it. Think about it like this. This is the smallest possible value for any corresponding subarray, right? Right? Can we say that? So you have to figure it out like this. You have to figure it out like this, that what should be the search space? Every time in a binary search question, all you have to figure out is the corresponding search space. Once you have the search space, then applying binary search is not that of a difficult task. So that's what we are also doing here. the highest possible value, the highest possible value that we are going to keep is going to be the sum of the subarray. And the lowest possible value that we can keep is the maximum element. Because just think about it. In this configuration, in this configuration, in this configuration, this configuration, the answer could have never been less than 5. Can I say that? Whatever would have been my answer could have been never less than 5. Can I say that? Just think about it. If let's say you have something like 1, 1, 1, 1, 5. So the answer can never be less than 5. It will be either more than 5 or less, or I would say something around that, but it can never be less than 5. So why it can never be less than 5? Because we have to always consider non-empty subarrays. That means at least subarray length will be at least 1, right? And if you just consider one single element, then the subarray with the biggest sum is going to be the maximum element subarray, right? So this will be considered, and hence the search space can be maximum element to the sum of the elements. And within this search space, I'm going to calculate a mid. This mid is our candidate sum. It will give us a yes or no answer. Yes or no answer means that are we able to split our array into k subarrays such that the largest sum is equal to or less than mid, right? So are we able to split the array into k subarrays such that largest subarray sum is less than or equal to mid? That are we able to divide our subarray, our array into multiple subarrays such that the largest sum of any subarray is less than or equal to mid? If you are able to divide it, then you can say this can be a possible answer, and we should try to reduce this value because we want to minimize this sum, right? So we will go to the left because we want to now reduce this mid value. But if you are not able to do it, in the split in mid value, you will never be able to do it in less than mid value. So always you need to increase the size of the sum. So you go right. Don't you remember that this is exactly the same thing we were doing in the container problem? If I show you the code for the container problem, right? Can you see? If we were able to do it, we go left. Otherwise, we go right. That's it. That's what we need. And can you see? The search space was also maximum weight to total weights. Isn't it? So the whole problem looks very similar. Here also we were getting total weight. This time total weight will be what? Total weight will be replaced by total sum. Total weight will be replaced by total sum. Can I say that? Right? So this is what we are going to do. So let's say for a moment, I'll modify this solution only. Let's say I'm not writing a new solution. I'll modify the same solution. Okay. I'll just change the variable namings here and there. So let's say I copy paste everything from here, paste it here, and copy everything from here, paste it here. Okay. So I have copy pasted everything. Okay, cool. We calculate total weight, we calculate maximum weight. This is what we have. We start applying binary search, and then we get the answer here. Now we'll just change the name of the function. We'll say can split into k subarrays with max mid sum. Okay, let's keep this as our value, that can we actually split, right? Okay, so you can see you have to split it into k non-empty subarrays. Can I say that? Right? You have to split it in k non-empty subarrays, right? And for each subarray, what you are going to consider? You are going to consider the corresponding sum, right? That is what is going to be your corresponding answer. Okay, so instead of days count, I'll say subarray count. I'll say subarray count plus plus. Subarray count. Instead of this d value, I'll take k and I'll compare it with k. And total weight can be replaced by total sum. Total sum. And this weights array will be nums array. So num inside nums. Num and num. Okay. More or less, the solution pretty much looks same. Can I say that? More or less, the solution pretty much looks same. Okay, I just changed the variable names here and there, nothing much. Okay, not making too much effort, and let's see whether we are able to submit it or not. If I run the code and let's see what happens. Okay, one more variable naming we have to change. This should be TS. This should be TS, total sum. And here also, this should be num inside nums. Okay, and variable name also I'm changing because otherwise maybe later if you will read the code, you will not be able to understand it well. This should also be nums. And yep, let's try to run the code now. And this D should also be converted to K. This D should also be converted to K. Okay. Yep. I guess that's the last update. And you can see just changing the variable names, we are able to submit the question. Let's try with one more test case. K is equals to 2. Run the code. Okay. Looks good. Looks good. Let's submit. And done. This question and the container question has no difference at all. Overall, there is no difference at all. It's the same question. The naming is different. 100% same. I just changed the variable names. I didn't change any logical part of the problem. And you can see it is working pretty good. For example, like now this time, let me not even change the variable names. Okay, copy, paste. Let's change it to weights and let's change it to D. Okay, and copy, paste, run the code, submit the code, done. It's the same to same code is working now. But again, like let's keep the modified code, but you can see it was the same question. In lead code, this is a common trend. They generally have a lot of common or same question or 90% same question. People generally just keep on banging their head but don't recognize the patterns that you have to actually just eventually change, and problems will get solved. And you can see it's a pretty direct question on minimax binary search on answer kind of a problem, and you know the logic pretty good. So I hope the overall logic is clear to everyone. If not, then I would highly recommend you to just again watch the part of capacity to ship packages question and then revisit this question again.
So this is a new problem coming in front of us. The problem says that this morning the jury decided to add one or more very easy problem to the problem set of the Olympiad. The executive strategy of the organizing committee has printed its statement in one copy. Okay, so the problem statement has been printed in one copy. And now they need to make n more copies before the start of the Olympiad. Now, n more copies need to be printed before the start of the Olympiad. Okay, cool. They have two copiers. Copiers is like a photocopy machine at his disposal, one of which copies a sheet in x seconds and another in y second. So there are two photocopy machines, M1, M2. M1 machine creates one copy in x seconds, M2 creates one copy in y seconds, right? Okay. It is allowed to use one or both copier at the same time, so you can parallelly run both of the machines. You can copy not only from the original but from the copy also. For example, there is let's say an original document. Okay, you can create copies from this original document, and if let's say you have created a copy of this document, you can create more copies from this copy also. So both of this original document and a copy document can be given as the input in the machines. Okay, help them find out the minimum time they need to take to make n copies of the statement. So what the problem is that there is an original piece of paper. For this original piece of paper, you need to create n copies. There are two photocopy machines. One photocopy machine
takes X seconds to print one copy. Another photocopy machine takes Y seconds to print one copy. In order to create the copy, you can use the original document also, and any other copy document also can help you to do a photocopy. You need to check what is the minimum time to make n copies with this configuration. For example, if let's say you need to make 4 copies and both of the machines take 1 unit of time for creating one copy, then you are going to take 3 unit of time. How? In your M1 machine and M2 machine, there are two machines. Initially, you have the original copy only. So you only have one original copy, right? You cannot pass the same copy in both of the machine at same time. So let's say what you will do, you will pass this copy in machine M1, and in the first second you will create a copy C1 of it. So after spending 1 second, you have the original document, of course, and one copy of it. Now you will parallelly supply these two together in M1, M2. So in the second, you will be having C2 and C3. Two more copies getting printed out from both of the machines. And in the third second, you'll be having one more copy from M1 because now you just need one copy. 3 copies are already there. Just run M1 and you will get your fourth copy. So C1, C2, C3, C4, all 4 copies can be there within 3 unit of time. Let's take one more example. If n is equals to 5, x is 1, y is 2. Okay. So now you need to create 5 copies. Now inside machine M1 and M2, first of all, M1 takes 1 unit of time and M2 takes 2 unit of time to print one copy. Now when you will start, you have an original document, right? You have an original document. Of course, you cannot pass this original document to both of them. So to run both of them parallelly, you need one more copy document. So now here, I am going to pass this original document in M1 because M1 machine is faster. If I will pass my original document in M2, to create the first copy, it is going to take 2 unit of time, whereas this will take 1 unit of time. So I'm going to pass my original document inside M1. If you pass your original document inside M1, in 1 unit of time, you will be having your first copy. So now you have the original document and the first copy in 1 unit of time. Now you pass both of them parallelly. You pass both of them parallelly. So after the second unit of time, what will happen? If you pass, let's say, the original doc to M1 and C1 to M2. Okay. So after the second or the second unit of time has elapsed, M1 machine will produce one more copy, C2. M2 machine will not prepare any copy because it takes 2 seconds. So half of the copy will be printed, half is still left. After third unit of time, M1 will create one more copy, C3. And this time M2 will create the first copy coming from C1, that is C4. Okay. Now for the last copy, I will just use M1 again and use my original doc. M1 will throw one more copy in the 4th second, that will be the 5th copy, and you can see 4 is our answer. That is, in 4 unit of time you will be able to print 5 copies. So given the configuration of the printers and the number of copies you need to find in how much minimum time you can actually print the n copies. N can be as big as 2 into 10 raised per 8. X and Y can be as big as 10. So now how can we solve this question? If let's say I need to create n copies, the most suitable way is going to be to run both of them parallelly. To run both of them parallelly, of course, I need at least the first copy ready with me. So to create the first copy, how much time you are going to take? You are going to take minimum of x comma y time. Whatever is minimum of x comma y time, in this much time you will get one copy. Can I say that? After this much time, all you need to do is now create n minus 1 more copies. You need to create n minus 1 more copies. Okay. Cool. Now, how can we create n minus 1 more copies is the question in front of us. Now just think about it. If let's say we consume 10 unit of time. In 10 unit of time, M2 machine, which is printing one paper in 2 seconds, how many paper it will print in 10 unit of time? Can I say it will print 5 copies in 10 unit of time? 10 by 2. right? So I can say that in z unit of time, m1 will print z by x copies, m2 will print z by y copies. Can I say that? Okay. And I need to find minimum value of z such that we can combine make n minus 1 more copies, because one copy has been already created in the best possible time. So I say that let's try to define a search space, because it looks like we have to do some minimization maximization. Let's at least try it in terms of binary search. There are other algorithms like DP and all that can also help you to in minimization and maximization kind of problems. But for the timing, looks like binary search can be a good way to go for. Let's try to define a search space. Now, what is the quantity that you need to find? The quantity is minimum time, right? Minimum time. You have to minimize the overall time taken. Can you tell me what is the bare minimum time that is definitely going to be spent? Doesn't matter how many copies you want to make. I can say that if n is 1, that is you want to just make one copy, then minimum of x, y, comma time is going to be elapsed. Can I say that? If we say that n is always going to be at least 1, right? At least one copy you have to make, then minimum time that your algorithm can anytime take is at least minimum of x comma y. Now what is the maximum time it can take? What is the maximum time it can take? The maximum time will be, you try to print all the papers with the slower machine. You try to print all the papers with the slower machine. Okay. So let's say whatever is maximum of x comma y multiplied by n. This much time will be the time that is going to be the highest possible one, right? Maximum time that can occur, because you are not using both the machines parallelly, you are using the slower machine. That's it. And in between this range only, my final answer is going to lie. So for example, for 512, for n is equals to 5, x is equals to 1, y is equals to 2, the search space will be minimum of x comma y 1, maximum of x comma y into 5, that is 10. So between 1 to 10 only my answer will lie. Now let's divide my search space into two halves and let's see if both of the halves are different based on some property or not. If we divide the search space into two halves such that this is the mid, let's see, can we print all the papers in mid unit of time or not? Okay. Can we print n minus 1 papers in mid unit of time? Okay. So let's see. If you want to print, if you have been given mid unit of time, let's see how much papers you can make. From machine M1, you will be able to make mid by x unit of paper. From machine M2, you will be able to make mid by y unit of paper. So you will check if mid by x plus mid by y is greater than or equal to n minus 1 or not. That is, in mid unit of time, can you print at least n minus 1 papers or not? If you are able to print at least n minus 1 papers in mid unit of time, you are definitely going to print all the papers in more than mid unit of time. Let's say I'm able to print all the papers in 10 seconds. I definitely will be able to print all of the papers in 100 seconds, right? So we are going to discard the right half and we will go to the left. But if we are not able to print all of them in n minus 1 unit of time, in mid unit of time, if you are not able to print all the n minus 1 copies, then I won't be able to print in less than mid unit of time. I need to go to the right side. That's it. That's all that you need to do in order to solve this particular question. So what you can do is low is equals to, let's say, minimum of x comma y. High is equals to n into maximum of x into y. Then you say while low is less than or equal to high, you say answer is equals to minus 1. you calculate mid, low plus high minus low by 2, and then you check copies is equals to mid by x plus mid by y, right? Mid by x plus mid by y. If copies is greater than or equal to n minus 1, that means in mid unit of time we were able to print at least n minus 1 copies. I need to find even lesser time. So this can be a potential answer, but I want to find something even less than that. So high is equals to mid minus 1. Else, if we are not able to print n minus 1 copies in mid unit of time, I won't be able to print it in less than mid unit of time. So I do low is equals to mid plus 1. Right? At last, what we are going to return? We are going to return answer plus minimum of x comma y. Why answer plus minimum of x comma y? Because this answer is to print n minus 1 copies, and one more copy we printed, the first copy in this much unit of time. So that much unit of time I'm adding, and that's the final solution that we can get. What will be the time complexity of the solution? The time complexity of the solution is going to be order of log of max of x comma y into n unit of time. That's it. Right? And max of x comma y, if you see, x comma y can be as big as 10, n can be as big as 10 raised per 8. So 10 raised per 8 into 10 is 10 raised per 9. Log of 10 raised per 9 is going to be approximately 30. So approximately in 30 iterations, you will very easily get the answer for the algorithm. And that's the power of binary search in front of you. So this is a new problem coming from Spodge. The problem name is A, B, C, D, E, F. The problem says that you are given a set S of integers between minus 3 into 10 raised to the power 4 to 3 into 10 raised to the power 4. Okay. You have to find the total number of 6 tuples A, B, C, D, E, F. What is a 6 tuple? 6 tuple is a collection of 6 numbers or 6 values such that A, B, C, D, E, F belongs to S, D is never equal to 0, and they satisfy this equation A into B plus C by D minus E equals to F, right? So for example, if let's say the given set of elements, let's say the first line will contain n, that is 2, and then there are two elements 2, 3, right? So let's say if there are two elements 2, 3, then you have to find in how many ways you can take 6 values out of the given set such that D is not equal to 0 and A into B plus C by D minus E should be equal to F. So one way can be, if you do 2 into 2 plus 2 by 2, this is what? 2 into 2, 4, 4 plus 2, 6, 6 by 2, 3, right? Or let's do this, 2 into 3, let's do 2 into 3. So 2 into 3, 6 plus 2, 8 by 2 is 4, minus 2 equals to 2. That is, you say 2 comma 3 comma 2 comma 2 comma 2 comma 2. This is one possible way. Another possible way is 3 into 2 plus 2 by 2 minus 2 equals to 2. That is, A as 3, now B as 2, and the remaining values also as 2. This is another way that you can figure out. Right. Okay. Apart from that, let's see what else we can do. So if we do, let's say 3 into 3 plus 3 by 3, this is what? 3 into 3, 9, plus 3 by 3 is what? 12 by 3. Okay, so let's do this. 3 into 3 plus 3 by 3 minus 2 equals to 2. See? 3 into 3, 9, plus 3, 12. 12 by 3 is 4. 4 minus 2 is 2. This is another possible way. Can I say that? Right. There will be one more possible way, I believe. I guess the answer is 4, right? So for this test case, the answer is 4. So there will be one more possible way. Let's try to figure it out. So if we do 3 into 2 plus 3 by 3, this is 6 plus 3, 9 by 3 is 3 minus 3. This will become, this won't work. This should be 3 into 3, 9 plus 3 is 12. Okay, this can be one more way. 3 into 3 plus 3. So 9 plus 3 is 12 by 2. 12 by 2 is 6. Minus 3 is equals to 3. This is another way. So in these 4 ways, you can satisfy the equation and every value is going to be derived from this array such that d is not equal to 0. So one value can be allocated to more than one, I would say, variables of the 6 tuple, and you need to count how many 6 tuples will exist. The length of the array, if you carefully see, the length of the array can be as big as 100. Okay. Length of the array can be as big as 100, but the elements of the array can be as big as minus 3 into 10 raised to the power 4, minus 3 into 10 raised to the power 4 to 3 into 10 raised to the power 4. So this is the problem statement in hand, that you are given a set of numbers. You need to count the number of 6 tuples such that the 6 tuples validate this equation and d is not equal to 0. Now, how can we solve this particular question? If you see this question, then the length of the array is given as big as 10 raised to the power 2. One brute force solution can be to generate all possible 6 tuples right. One brute force solution is going to be to generate all possible 6 tuples, right? Now, if you have to generate all possible 6 tuples, if you want to generate all possible pairs, then it takes us n square. If you want to generate all possible triplets, it takes us n cube. If you want to generate all possible 6 tuples, it is going to take us order of n raised to the power 6. Can I say that? Right. You'll do something like I is equals to 0, I less than n, I plus plus. Then j equals to 0, j less than n, j plus plus. K equals to 0, k less than n, k plus plus. And let's make it, instead of I, j, k, let's make it a, b, c, d. A, b, c, d equals to 0, d less than n, d plus plus. Then e equals to 0, e less than n, e plus plus. F is equals to 0, f less than n, f plus plus. Right. You're going to write this nested loop for n raised power 6 time, and you have to also put a check that if d is not equal to 0, then only you apply this loop. But my point being that in the worst case, the value can be as big as order of n raised to the power 6. N is 10 raised to the power 2. So 10 raised to the power 2 whole raised to the power 6 is 10 raised to the power 12. This solution is going to give us time limit exceeded. We won't be able to submit this particular question. So generating all the possible 6 tuples is not going to help us. Now, generally, in the kind of questions where you have an equation, it really helps to solve the equation a bit, because maybe the I would say trivial form of the equation helps us to understand something. So if I just simplify, the equation, this will become a plus b into c by d is equals to f plus e, such that d is not equal to 0. And then a plus b into c equals to d into f plus e, such that d is not equal to 0. This can be considered as the simplified equation, right? This can be considered as simplified equation. You need to find all possible 6 tuples a, b, c, d, e, f that now satisfies this equation such that d is not equal to 0. Now, don't you think we have 3 values on one side and 3 values on the other side, right? And if you have an array, we already talked about that in the example. If you have an array, then one value can be allocated to multiple values, right? And I guess this is A into B plus C. Okay, let's just confirm it. A into B plus C. Okay, so A into B plus C by D minus C equals to F. A into B plus C equals to FE, right? A plus A into B. This should be A into B plus C. Okay, but my point being that we are able to allocate 3 values on one side, 3 values on other side. How about if we think in terms of triplets? How about if we think in terms of triplets? Because we have 3 values on one side, 3 values on one side. If we are able to find all possible pair of triplets, A, B, C, D, E, F, right? One triplet is this, one triplet is this. This is a pair of triplet such that they satisfies this equation along with D not equal to 0. Then all those pair of triplets are going to actually form our 6 tuple. Can I say that? Now, the solution that I'm proposing here is that, let's say you have an array 2, 3, right? Let's try to form all possible triplets of 2, 3. What are the all possible triplets of 2, 3? 2, 2, 2, 2, 2, 3, 2, 3, 3, 3, 3, 3, right? See, 2 taken all the times, then these 2 along with this 3, then this 2 here and this 3 here, right? And this should be 2, 3, 2. Okay, 2, 3, 2, and then 2, 3, 3, 2, 3, 3. Then you will be having 3, 2, 3, right? Or 3, 2, 2. Then you will be having 3, 2, 3. Then we will be having 3, 3, 2. Then 3, 3, 3. Right? All these possible triplets will be there. Okay, all these triplets will be there. I'm saying let's compute these triplets. And actually, instead of just computing these triplets, let's compute it in the form of A into B plus C and D into F plus E. Right? So what I'm saying is that let's prepare 2 arrays, LHS as one array, RHS as one array, and we say for A equals to 0, A less than N, A plus plus, for B equals to 0, B less than N, B plus plus, for C equals to 0, C less than N, C plus plus, we say LHS dot push ARR of A into ARR of B plus ARR of C. Okay. Let's have one cubic loop. This is order of n cube, right? What that loop is going to do on our given array ARR, let's say 2, 3, it is going to form all the possible triplets and then allocate those triplets to each other, verifying this equation, right? So let's say one triplet is 2, 2, 3, then it will be 2 into 2 plus 3 getting added inside LGS. So actually we are going to store all possibilities of A into B plus C inside the LHS array. Whatever are your total number of possibilities for A into B plus C from this given array, you are going to store that inside LHS. And the same thing you are going to do with RHS. For D equals to 0, D less than N, D plus plus. For E equals to 0, E less than N, E plus plus. For F is equals to 0, F less than N, F plus plus. If ARR of D is not equal to 0, RHS dot push ARR of D into ARR of E plus ARR of F. Okay. Right. So we'll be writing another cubic loop. We'll be writing another cubic loop such that we store all the possible values of d into e plus f inside RHS. D into e plus f inside RHS. Right. So how this is going to help? How is this going to help? If let's say you have an array 2, 3, there will be a lot of triplets. As I said, one triplet is going to be 2, 2, 2, one triplet is going to be 2, 2, 3, one triplet is going to be 2, 3, 2, one triplet is going to be 2, 3, 3, and so on. If I allocate it to a into b plus c, this will become 6, this will become 7, this will become 8, this will become 9, right, and so on. A lot of values are going to be inside LHS. And the same if you do d into e plus f, right? So if this becomes d e f, so this will be 4 to 8, then 10, then 10 again, 12, and so on. A lot of values will be there inside RHS. So this is going to be your LHS, this is going to be your RHS. Now what do you need to do? You need to find all the pair of triplets, like two set of triplets that satisfy this equation. And can you see that there will be some common elements here? See, this 8 is common here, right? Now you have an array LHS, you have an array LHS, and you have an array RHS, right? What do you need to find? You need to find that for each value of LHS, how many same values we find in RHS. For each value of LHS, how many same values we find in RHS, right? For example, I'm just giving you an example. I'm not sure whether this will be your final array or not. So now let's say that this is LHS, this is RHS. Actually, I actually computed both of the possible triplets, right? Inside LHS, I have all the occurrences of a into b plus c. Inside RHS, I have all the occurrences of d into e plus f. Now you can see both of them are unsorted. What you need to do for each occurrence of LHS, you need to find how many of them also exist in RHS, right? For example, does 6 exist in RHS? No. 7 exist in RHS? No. Does 8 exist in RHS? Yes. There is two pairs of 8 that we can form. So this 8 is formed by one triplet, this 8 is formed by one triplet. That means we have a pair of triplets such that a into b plus c is equals to d into e plus f. So this is going to contribute to my answer. We got one particular count. Then 9. Do we have 9? No. This 8 again. See, this 8 is again going to be paired with this 8. So we found one more answer. Do we have 9? No. Do we have 11? No. Do we have 12? Yes. For this 12, I have two occurrences of 12. That means for this particular triplet, there exists two different triplets such that the value is going to be same. So I'll add plus 2 to it. This will become 4, and 4 is our answer for the test case of 2, 3. Right. Now the only problem left is that once you have computed these two LHS RHS array, how can you find every element of LHS inside RHS efficiently? Now let's see how much time we have spent up till now. We use this for loop that is order of n cube. After the completion of this for loop, we use this for loop that is order of n cube. So we have already done n cube plus n cube plus. Now, if you sort the RHS array, if you sort this array, this will become what? Actually, it is already in the sorted form only, but we can't be sure. For example, LHS is not in the sorted form. So let's say we sort the RHS array. Now, what will be the length of the RHS array? Now, it is containing all the possible triplets, right? How many triplets can be there? N cube triplets. So n cube log n cube. This much time you are going to spend in sorting the RHS array. Once the RHS array is sorted, then for each element of LHS, you can apply binary search. You can calculate the lower bound and upper bound, right? You can calculate the lower bound and upper bound. Okay. So for example, for this 12, the lower bound is going to be this 12, the upper bound is going to be 15. So whatever is this index j, whatever is this index I, j minus I is going to give you number of occurrences of 12. Now for each element of LHS, I will do 2 times binary search. So 2 times for each element. How many elements are there? N cube. You are going to do binary search on RHS. The size of the search space is the RHS array, and the length of the RHS array is N cube, log N cube. Right. If you see, this is a lower degree term, lower degree term. This becomes 3n cube log n cube, which will be approximately what? 3 into 3 n cube log n. This is constant. So time complexity is n cube log n. The space complexity is order of n cube. And what will be n cube log n? So n is 10 raised to the power 2. 10 raised to the power 2 raised to the power 3 is what? 10 raised to the power 6. Log 10 raised to the power 2 is going to be approximately 10 raised to the power 7. This solution will be submitted, and we will be able to solve this question very easily using binary search. Right. So this is going to be the overall coding implementation, and I would say the overall logic that you can apply in order to solve the question A, B, C, D, E, F from Spodge. So now we are going to start the discussion on a new problem, that is median of two sorted arrays. So we need to first of all understand the problem, that what the problem says and what the problem expects. So the problem says that we will be given two sorted arrays, right? So we'll be given two different arrays which will be completely sorted, and when I say sorted, they are going to be arranged in ascending order, right? So we'll be given two sorted arrays, and our task is to find the median of these sorted arrays, where the number of operations, or not operation, but let's say where the number of elements in the first array can be different than the other. So this is the problem statement for us. That we will be given two sorted arrays, right? Now what we need to find, we want to find the median of these sorted arrays. Now we don't want to find median of individual arrays, right? We don't want to find median of first array separately and second array separately. No. Our agenda is, if we will be combining both the arrays, then what will be the median of the combined data that we are going to have by combining both the sorted arrays. And the length of both the arrays can be different also, right? The first array can be of different length, second array can be of a different length. So that's what we have to do. For example, let's say you have something like 7, 12, 14, 15, and 1, 2, 3, 4, 9, 11. For this, the answer is going to be 8. Now, in order to understand how the answer comes as 8, we need to first of all understand what is median, right? We need to first of all understand what is a median. So let me open an article in front of you guys that can easily help you to understand what is median. Okay, so you can see the median is the middle value in a set of data. So if you are going to have a set of data, median is going to be the middlemost value. First, organize and order the data from smallest to largest. That means arrange your data in ascending order. Now to find the midpoint, divide the number of observations by 2, that is the total number of entries, by 2. If there are an odd number of observation, round that number up and find the value in that position, and the value in that position is going to be the median. So let's say that if you have a set of data like 10, 1, 6, 3, 5, Then what you're going to do, you're going to arrange this data in ascending order, that is 1, 3, 5, 6, 10. And then you're going to find the middle value. So the middlemost value is 5. So for this data, 5 is the median. If let's say there are even numbers, in odd number you can find one median, but what about even numbers? There are two elements in the middle. In that case, median can be dependent on problem to problem. So some examples expect the median to be average of the two values. For example, let's say you have a data like 10, 1, 2, 3, 5, 6. The sorted arrangement will be 1, 2, 3, 5, 6, 10. And both of these are going to be the middle element. Now, in few problems, the average of the middle element, that is 5 plus 3 by 2, that is 4. 4 is the median of the data. Sometimes you take the smaller value of the middle, or sometimes you take the larger value of the middle. Depends on problem to problem, but median is the middlemost point of the given set of data. So you have to arrange that data and then get the median. So in this data, we want to find the median. If you combine this data in a sorted order, it will be 1, 2, 3, 4, 7, 9, 11, 12, 14, 15. This is going to be the data. If you see, there are like 4 elements here, there are like 4 elements here, and there are like 2 elements here. So total 10 elements are there. If you have 10 elements here, then the median is going to be what? Average of the middle two. So 7 plus 9 by 2 is going to be 8. So 8 is our answer. 8 is our answer. So you will be given two separate arrays. You have to combine the data of the two arrays and then find the median. In this case, if you combine and then arrange them in sorted order, because the easiest way to find a median is just arrange your data into sorted order and then try to find your particular answer. So if you arrange this data in a sorted order and then calculate the middlemost value, if the data is even, then you have to take the average of the two middle values. If the data is odd, just return that direct value and you will get your median. This is the expectation from the problem. Now the length of each array, let's say the length of this array is n, the length of this array is m, n comma m is going to be less than or equal to, let's say 10 raised to the power 6. This is a constraint that we can keep, right? Based on this constraint and these kind of examples, we have to think that how can we solve this problem, right? We have to clarify, like define a logic that how can we solve this problem. Before we move forward, I would recommend you guys to think about it first, and then only it would make sense for us to discuss this problem, right? So what can be the brute force? What can be the brute force solution? Brute force. The brute force solution says that just do what the problem is expecting you to do, right? Merge the arrays. Merge the arrays in the first step, that is just place, or not even, don't even merge. Yeah, like you can, in the worst brute force case, you can say place second array after first array, right? That is place both of them side by side, then sort this combined data, sort this combined data, and the third, return the mid. Okay, these three steps can be the brute force. So if let's say the first array is of length n and the second array is of length m, what you're going to do, you're going to place the array of length m after the array of length n. So you will get an array of length n plus m. Now you want to sort it. Sorting an array of length n plus m, right? If you're not able to see, I can push it here. Sorting an array of length n plus m is going to be n plus m log n plus m. Order of n plus m log of n plus m, right? This can be the worst brute force, like do what the problem is directly saying. Now we can optimize this solution as well, because both the arrays are sorted. We want to combine them and get and then again sort the combined data. Instead of combining them and again sorting the data, what we can do, we can use the algorithm of merge two sorted arrays. In order to optimize, we can merge the two sorted arrays. If one array is of length n and another array is of length m, then merge two sorted arrays is going to work in order of n plus m. And this merged array is going to be already sorted. Merge two sorted arrays algorithm of merge sort. We are going to use it and the final array will be already sorted. After that, just return the middle. Okay. We'll just return the middle. So the time complexity of this approach is going to be order of n plus m. So from n plus m log n plus m, you have optimized your solution to order of n plus m, right? Okay. So we need to see how can we optimize. How can we optimize? In order to optimize the solution, we need to have a simple observation. The observation is going to be in our final sorted array, median is the middlemost element, right? In our final sorted array, the median is going to be the middlemost element, I can say that. So the number of elements to the left of mid is going to be equal to number of elements to the right of mid, right? If you try to find the median, then median is going to be the middlemost element. Now, if this is the middlemost element, then elements to the left side of it is going to be equal to the number of elements to the right side of it. Like there will be an equal partition that will happen due to the median, right? So what we can say is that if let's say this was our array, then if this is the median and this is the partition A and this is the partition B, then can we say that the length of the partition A is going to be equal to the length of the partition B? This is something that we can directly write. Okay. Now, the given arrays, let's say the given arrays were A and B. Just a second. Let's say this is our array. Okay. Now I am saying in the given arrays also, I'm going to make two partitions, xy and xy. xy, xy. Right. We did this partition. We know that in the final array, when the partition will happen, then the situation will be that your array will be divided into two parts with equal lengths. Now I am saying these are the two given arrays. These are the two given arrays. In these given arrays also, I want to make some partition. Now you might be thinking why I'm making this partition. Now what I can say is that our final array is going to be what? A merger of A and B only, right? The final array from which we have to calculate the median such that the whole array is sorted and has the combination of the data of both the given arrays. That's going to be what? That both of the arrays are going to go through the merge algorithm and then you are going to get your final array. Can I say that? Right. So if let's say C is the final sorted array, right? This is the final sorted array. Then in the array C, before the median, let's say this is the median somewhere. Whatever elements we have before the median and after the median, Then in this region, some elements from A and some elements from B will be there. Can I say that? When we will be merging them in sorted fashion and we will calculate our median, then on the left side of the median, some elements will be there from array A and some array elements will be there from array B. For example, let's say in the given test case, we did this merging. Now this, both of these as a combination is going to give you a median. Let's say you were having one more element, let's say 8 here, 7, 8, 12. Then we were having 8 also here. Now if you see, if you have 8, then this is the left part. In the left part you have 1, 2, 3, 4 that is coming from the second array, and you have 7 that is coming from the first array. So, and the same thing is going to happen on the right side also. So the left side is also going to have some elements from the array A, and the right side is also going to have some elements from array. Same thing for left side, that some elements apart from A, there will be some elements from B also, and then there will be some elements from B on the right side also. So there will be combination of elements from both the array A and B on the left side as well as the right side. This is a very crucial observation that we have to derive. So after merging in sorted array, in sorted fashion, before median, we will be having some elements from A and some elements from B will be on the left side, will be on the left of median. Right. And similarly for right side. So what we can say is that if let's say, if we say that some elements from A and some elements from B are going to be on the left side, so we can say some AX elements and BX elements will be on the left side, and some AY elements and BY elements are going to be on the right side. Let's say this is the partition that you are going to get in the two arrays, such that everything from to the left of this partition in array A and array B are going to get combined to form the left side of the median, and same thing here for the right side of the median. And this partition doesn't need to be equal. This can be different in length. For example, in the given test case also, if you have a 8 here and you got a 8 here, then there are 4 elements getting contributed by the second array, but only 1 element getting contributed by the first array. So the contribution can be different. That is the number of elements that the array A is giving to the left side of median can be different from the number of elements that array B is giving. But my point is, some elements from A and some elements from B together will form the left side of the A, and some elements from A and some elements from B together will form the right side of median. Right, this is something that we have to carefully analyze. So even if we take one more example, let's say A is, I'll give you a general example, x1, x2, x3, x4, x5, x6, and B is like y1, y3, y4, y5, y6, y7, and let's have one more y8. Y8. Okay. Now, in your final array, there will be some median. There will be some elements to the right of median. There will be some elements to the left of median. So let's say we can say that y1, y2, x1, y3, y4, x2, and let's add one more element. Let's say y5. Let's say all of these elements are on the left side, and x3, x4, y6, y7, x5, y8, x6. Let's say these are the elements on the right side. If you count the elements, you can see 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You have equal amount of elements on both the sides, right? this is going to be an equal partition on the both the sides, right? Let's say somewhere here we were having the median. So from the left of median and the right of median, you have equal amount of elements, and the left side is prepared by some elements from X and some elements from Y. Same thing for right side as well. This is going to be a typical representation of our final C array. This will be the C array. This will be the final C array with some X. So here you can see X1 and X2, only 2 elements from X are there and 5 elements from Y are there. These two are going to combine the left side, and these two are going to combine for the right side. Can I say that? So this is a very important property. Now, let's do it like this. Let's put a partition here and let's put a partition here. That means inside the array A, we are going to have only these two elements contributing to the left side of median, and inside array B, we are going to have these 5 elements to contribute to the left of median. So we can say that if we put a partition here and if we put a partition here, then these two are the left sides and these two are the right sides. Okay, these two are the left side and the right side. So now let's say this length is M, or let's say this length is, let's say I, and this length is J, right? So can I say I is plus J is going to be equal to what? Like this I is the length of this partition, J is the length of this partition. Now if we try to sum up I and J, can I say this is going to be equal to the length of the remaining arrays? That is M minus I plus N minus J, because this is going to be M minus I, this is going to have N minus J, right? So this plus this, that is the length on the left side, is going to be the length on the right side. So we can say length of the left side is equals to length of the right side. Okay, this property is clear to everyone, right? And array A's length is going to be defined as AM, and this is BN. This is we need to make sure. Now one observation is ready for us. This observation is ready for us. Okay, now we can say that length of array C will be M plus N. Can I say that? Because C is the combination of both of them, right? So we can say the length of the array will be M plus N, and median will lie on the position M plus N plus 1 by 2. Can I say that? That is on the middle point. This will be your median. That is the middle point. If M plus N is the whole length of the array, then we can say M plus N plus 1 by 2 can be the median, right? Just think about it. If let's say the first array is of length 3, the second array is of length 5. So this is going to be what? Even, right? So 5 plus 3, 8 plus 1 by 2. So 4 plus 1, 8 plus 1 is 9 by 2, which is 4.5, which is 4 only. If let's say this array is of length 6, then 3 plus 6 plus 1 by 2 is what? 9 plus 1, 10 by 2, that is position 5. Right? So somewhere around here, we are going to have our median. Right? Somewhere around here, we are going to have our median. My point is, irrespective whether you add M plus N by 2 or M plus N plus 1 by 2, this is just to make calculation simple. This is going to denote your middle point. Middle point. Like we are first of all writing all the observations so that we can come to a conclusion. This middle point is going to be the point where you are going to find your median. Okay. So these are the two observations that we have made. Okay. Now, if we know how many elements from array A are going to contribute to the left of median, then we can easily calculate the number of elements that will participate on the left side of median from array B. Can I say that? Can I say that? My point is, if anyhow any cost, you know that how many elements from array A are going to contribute to the left side of median. If let's say you know this, then can you not directly calculate how many elements from the array B are going to be on the left side of median? You might be thinking how we can do this. Just think about it. We know that the length of the array is going to be m plus n. So half of the elements are going to be what? M plus n by 2 kind of thing, or m plus n plus 1 by 2 kind of a thing. Now, these are going to be like half of the elements. That's why this is the half position. So if you know how many elements, or how many elements are going to be on one half of the array, and from those half elements, you know how many elements are going to come from A, then can I say you can just directly calculate how many elements are going to come from B by subtracting the number of elements from array A from n plus 1 by 2. Let me repeat. So we know length of final array. We know the length of final array, that is m plus n. So we also know how many elements on left half of the array, that is m plus n by 2, or you can say m plus n plus 1 by 2, whatever you want to say, just to make calculations easy. Now, if you say number of elements in A which will be part of left half is x, then number of elements in B which will be part of left half is m plus n plus 1 by 2 minus x, because these x elements from A and let's say the remaining elements from B are going to contribute to the half of the array. This is an observation that we can make. So if we write it as, let's say, A is A1, A2, A3, A4, A5, A6, B1, B2, B3, B5, B6, B7, B8. Now let's say if we put the partition like this, now how many elements are these? 6 elements. How many elements are these? 8 elements. 8 plus 6 is what? 14. So on one half there will be approx 7 elements, and on one half there will be approx 7 elements. And because this is median, this is even, then apart from the median there will be 6 elements on the left and 6 elements on the right. So, and if you even include the median, then half partition you are going to make, that is 7 on the left and 7 on the right. So now if you know that 2 elements are on the left side from A, that is from A you are getting a contribution of 2 elements, and total element should be 7. So I can directly say that other 5 elements are going to come from B. If we fix that how many elements from A are going to come on the left side, and we know there will be 7 elements on the left side, then we can say there will be 5 elements that are going to come from B, right? This is going to be simple. This observation is going to be extremely simple. Can I say that? So now if we know all of these facts, whatever we discussed previously, and let's say this partition and this partition is the correct partition, that is, in our median, all of the elements are going to be coming from only these two partitions on the left and these two partitions on the right. Like if let's say these two are the correct partitions, like finally somehow we reached the correct partition, then can I say that if we reach the correct partition, then can I say, of course, A2 is less than or equal to A3. This is because array A is sorted. And B5 is less than or equal to B6 because array B is sorted. This is going to be true, right? Because array A is sorted, this is smaller, this is greater. B5 is smaller, B6 is greater. But we can say and because A2 is going to come on the left side of the median, can I say A2 will be less than or equal to B6 also? And B5 should be also less than or equal to A3, right? Why I am saying this? Let's see this again. Because the array is sorted, both of the arrays are sorted, so of course A2 and A3 are going to follow this relation that A2 will be less than or equal to A3, and B5 and B6 are going to follow this relation that B5 is less than or equal to B6. Okay, that's cool. But now we just said that before the median, from array A, only these two elements are going to contribute because this is the correct partition, and these 5 elements from B are going to contribute. So can I say that if B6 is going to be on the right side of the median and A2 is going to be on the left side of the median, A2 will be always less than or equal to B6. And same thing for B5, that if B5 is always on the left side of the median and A3 is always going to be on the right side of the median, then B5 is always going to be less than or equal to A3. Like these four, I would say, inequalities, in which two of the inequalities are coming due to the fact that the array is sorted, and the other two inequalities are coming due to the fact that we kept a median and we divided the array into two parts, both of the array into two parts, maybe unequal, but we are going to get this relation, right? So we can say that if this is the median, then A2 and B5 are going to be the rightmost element from the left side, and A3 and B6 are going to be the leftmost element from the right side, right? These are going to be the rightmost of left sides. Like any one of these two will be the rightmost of the left side, and these will be leftmost of right side, okay? And they are going to follow this relation if these two partitions are correct, right? So these relations will only work when the split is correct. Now we have one more observation based on these inequalities. Previous observation was this, and the new observation is this. Now, based on these two observations, can we do something? Is something that we have to figure out, right? Now we know that if we are able to set both of these partitions correctly, we will be able to get the median. We don't know how to set these partitions. So can I say that let's try to move this partition in array A. Somewhere we will try to move this partition in array A. Just like how you move the partition in array A, you will automatically be able to calculate the partition in array B. And once you move the partition somewhere, you can check if these four inequalities work or not. If they do not work, then maybe we need some more movement. If they work, then we can say that they might work, right? So we can say that during the partitions, we can check for the inequalities, right? If they work, then we have the answer, otherwise not. Otherwise not. And the best part is we don't need to move partition in both of the arrays. We can just move this partition somewhere in the array A, and let's say we fix this partition, let's say here. Then based on this partition, you know that okay, now we have 4 elements. On the left side of the median, there will be always 7 elements. So if 4 are going to come from here, that means 3 will come from here. So in the array B, the partition will be here. So if you move the partition in array A, you will automatically be able to calculate the partition in array B due to this property. And while moving, you can check about the inequalities, right? Now all we have to do is just see that how the movement is going to be done inside A. How we can do the movement inside A, that is something that we have to figure out. Okay. Now let's say if A2 is not less than or equal to B6. Just think about it. If this element is greater than B6, when this element will be greater than B6? This element will be greater than B6 when you are not having partition on the correct place. So where the partition should be? Where the partition should be? We want the partition to be somewhere such that A2 should be less than equal to B6, or whatever element is to the left of the partition should be less than or equal to B6. So we need to shift the partition to the left. Why we need to shift the partition to the left? If A2 is not less than or equal to B6, that means A2 is greater than B6. And we need to reduce A2. If we will be able to reduce A2, then only A2 will become less than this value. So we need to move this partition on the left side. Now, because A2 is more than B6, we need to reduce its value. So we go left. Okay. And if B5 is not less than or equal to A3, then just think about it. If B5 is not less than or equal to A3, then A3 is lesser, right? That means B5 is greater than A3. That means we need to increase A3. How can you increase A3? When you will move your partition to the right, then let's say partition comes here, then this value will be increased. So now A3 is less than B5. So we need to increase it. That means move partition to right. And you guys are able to see, right, that how the two observations are going to help us now, because now we don't need to move the partitions on both the arrays simultaneously. We can just move our partition here and there inside array A, and we will get the correct partition based with respect to the partition on array A inside array B by this length property. And because we know that these inequalities are going to always work, whatever partition we have, we can check whether this partition is correct or not. So let's say if this inequality, these two inequalities will always work because the arrays are sorted already. Now, if this inequality doesn't work, that means A2 is greater than B6. If A2 is greater than B6, we need to reduce A2. So we'll go to the left. If this inequality doesn't work, that means A3 is less than B5. If it is less, then we need to increase it. So we will move the partition to the right, and so on and so forth. This approach is going to help us to prepare the correct partition. Using this, we will be able to make correct partition on A array A, and then based on that partition, we can get partition on array B. Okay, this is going to be our final solution. Let me revise everything, whatever we have discussed till now. So what I said was, we need to look at optimizations. I am saying in our median, everything to the left will be equal to everything to the right in terms of the length. That is, the number of entries on the left side of median is going to be equal to the number of entries on the right side of the median. So I say that the left side entries, some entries are going to come from A, and then some entries are going to come from B. Same thing for right side. Some entries are going to come from A and some entries are going to come from B. So what we can say is that if, let's say, the number of entries from A to the left side of median is I, and from B to the left side of median is J, then I plus J is going to be equal to M minus I plus N minus J. That is due to length of A equals to length of B, that length of left part is equals to length of right part, right? And we can say that the length of array C will be M plus N, the final array C will be M plus N, and we know that half of the array is M plus N plus 1 by 2. That's the middle point. So if we know how many elements are there inside array A on the left side, that is I, then we can calculate the value of J very easily, because I plus J is going to be equal to M plus N plus 1 by 2. So if we know how many elements will be there on the left side, and we know what is the value of I, that is the number of elements from A, we can easily calculate J by doing M plus N plus 1 by 2 minus X. So if we know the correct partition in A, then based on that we can immediately calculate the partition in B. That's the first property. And if, let's say, this is the correct partition, then A2 and B5 are going to be the one rightmost element from the left side. One of these elements will be the rightmost element from the left side, and A3 and B6 will be the leftmost element on the right side. So they should follow these properties, these inequalities. Now, because the arrays are sorted, A2 will be definitely less than or equal to A3, B5 will be definitely less than or equal to B6. But apart from that, because A2 is always going to lie on the left side of the median, A2 should also be less than or equal to B6. And because B5 is always going to lie on the left side of the median, B5 should also be less than or equal to A3. If these four inequalities are set, we will be able to find the median. Now, my point is, how about if we start manipulating the partition inside array A and see whether this inequality is working or not. If not, then we can move the partition, because once we have set the partition somewhere in A, we can definitely calculate where it should be in B. So if this inequality doesn't work, that means A2 is greater than B6. If A2 is greater than B6, we need to reduce this A2, that is, reduce this contribution of A. So we need to go to the left. Otherwise, we need to go to the right. This is going to be the logic for the whole problem, that is calculating the median of two sorted arrays. So now let's just take an example and see how both of the properties are going to work together. So let's say we have 7, 12, 14, 15, and let's keep it like 7, 8, 12, 14, 15. And let's say we have 1, 2, 3, 4, 9, 11. Okay. So we got 5 elements here, we got 6 elements here. Okay, cool. Now, I am saying, let's keep the partition anywhere. For example, let's say I keep the partition here. Let's say I keep the partition here. Okay. Now, you know, here we have 5 elements. Here we have 6 elements. Total elements are what? 11. So on the left side of the median, there will be 5 elements. On the right side of the median, there will be 5 elements, and then there will be the median. Can I say that? Okay. Now, if, let's say, you are going to have 5 elements on the left side of the median, so if I say 4 are going to come from here, then can I say the partition inside B, the partition inside B will be here, because 4 plus 5 should be this. 4 plus 5, 4 plus 1 is 5, that is going to be the left side. Now we will check the inequality. Is 14 less than or equal to 2? Is 14 less than or equal to 2? This is what condition? This is the condition of is, sorry, 1 second. Yep. So this is the condition when we are checking if A2 is less than or equal to B6. No. No. If that's not the case, then how this condition will be hold true? When the partition will be slightly less. So for example, partition comes here. Partition, for example, comes here. So now you have 2 elements. That means 3 elements will be coming from B. Okay. Now you check 8 and 4. Is 8 less than or equal to 4? No. Oops. That means we need to decrease the value even further. Let's say we go here. Now if we have 1 element here, that means we need to have 4 elements here. Now, is 7 less than or equal to 9? Yes. So we need to find this first value, which is solving this inequality. And the other inequality is 4 should be less than or equal to 8. That is also correct. Yes. So this is how the movement is going to work. And you see 7 and 1, 2, 3, 4 are going to be on the left side of the median because median is 8. So 12, 14, 15 and 9, 11 are going to be on the right side. So we just see with respect to the left half, median and the right half are already going to get managed separately. So this is going to be the approach in order to solve the problem, for which we are going to see the coding implementation now as well. So let's just see how can we implement the coding implementation here. And based on the coding implementation, we will be able to easily decipher the time complexity also. The time complexity is going to be extremely efficient. Let's see. First of all, let's write a function median of 2 sorted arrays. Okay. Now let's say we are going to pass the array as A and B. Okay. Let's calculate the length of the array A. Let's say array A's length is M, and let's say array B's length is N. So we have the length of both the arrays. Okay. Now we can say that let low is equals to 0. We are going to apply binary search, and this binary search we are going to apply on what? Array A. So high should be equals to, let's say, M. Okay. We are going to put, because the partition we are going to move only on array A. So if we are going to move the partition only on array, we need to find the correct position of the partition. That position we can find using binary search. So we say that while low is less than or equal to high. Okay. Cool. So now what we are going to say is we are going to initialize few variables. Now whatever we have done, I'm going to just write everything as it is and things should work fine. So we'll say that let partition of M is going to low plus math.floor I minus low by 2. Okay. So I said that I'm calculating the midpoint. I'm calculating the midpoint in array A. This is midpoint in search space of array A. Okay. So we got this midpoint. Now this midpoint is technically the partition that we are putting inside array A. Now if we know where the partition inside array A is, can we calculate the partition inside array B? Yes. So you can say partition, let's, instead of saying this M, let's say this as A. Let's say this partition in B. Where the partition in B will be there, we can say math.floor M plus N plus 1 by 2 minus partition of A. So based on this formula, we can calculate where the partition of B should be present. Okay. Now we have both the partitions with us. Now we need to check if the inequalities are working or not. Okay. So we will say that we'll create 4 variables. We'll say max left of array A, then max left of array B, then min right on array A and min right on array B. I hope the variable names are explaining themselves, that max left of A is going to denote inside the array just before the partition what's the maximum element. Inside array B just before the partition B, what's your maximum element. Then inside array just to the right of partition, what's the minimum element, and same thing for B. So we have four values. We are going to set these values. Okay. Now if the partition of A is at 0th position, can I say there are no elements on the left? If the partition is at 0 position, that means you don't have any elements on the left, right? So we will say max left of A is equals to minus infinity. That means you don't have a maximum element. The maximum element that you have is minus infinity. Else, what will be your maximum element? Your maximum element is going to be A of partition of A minus 1. This will be your maximum element on the left side of the partition inside array A. Now the same thing. If partition of B is equals to 0, that means there are no elements on left of the partition in B. So we say that max left of B is equals to minus infinity. Else max left of B is equals to B of partition B minus 1. Simple, right? We have to see what are the elements just to the left of partition in A and just to the left of partition in B. If the partition is at position 0, that means you don't have anything on the left. So your max is minus infinity. Otherwise, your partition minus 1th index is going to be the element on the left, which is max. So we have set two variables. Now, time for the other two variables, that is min right A and min right B. Okay. So we say that if partition inside array A is equals to the last, like the partition that you are doing inside array A is at the last position. So you don't have anything on the right. Can I say that? So we can say min right of A is equals to plus infinity. Min right of A is equals to plus infinity. Else min right of A is equals to A of partition at A. Simple. And then the same thing, if partition of B is equals to n, then min right of B is equals to infinity. Else min right of B is equals to B of partition at B. That's it. So now we have all the four elements ready with us. Okay. One second, let's see. Let's see if there should not be any inconsistencies in the video. Okay, this is also correct. Min right B is also correct. Okay, let's see. Now we have all the four variables ready with the values. Now we check if max left of A is less than or equal to min right of B and max left of B is less than or equal to min right of A. If both the third and the fourth inequality, that is these two, if both of these two works properly, we can say we found the median. So we'll say that if m plus n mod 2 is equals to 0, that means you have an even length array. Otherwise you have an odd length array. So for both of them answer is different, right? Odd length array. For an even length array, what is the answer? For an even length array, we are going to return math.floor of, we can say, now if the elements are even, that means you got the correct partition, and now A2, B5, B6, A3. These are the four elements which are solving this inequality. Now, which elements will be there which are the middle two elements? Can I say the maximum of these and the minimum of these? Let's say the maximum of this is B5 and minimum of these is B6. So B5, B6 are the middlemost elements. So we can say math.max of max left A comma max left B plus math dot min of min right A comma min right B, okay, and then whole by 2. This whole by 2, okay. Otherwise, if you have an odd length array, this is an odd length array, that means we are going to return math dot max of max left of A or min right of max left of B, sorry, max left of B. So this if check will be executed when both of the inequalities are working. If it is not working, else if it is not working and max left of A is greater than min right of B, that is this condition. This condition, max left of A is greater, that means it's not less than or equal to B6. Then in this case, what we have to do, we have to go to the left. How do we go to the left? We say high is equals to partition of A minus 1. Else we have to go to the right, low is equals to partition of A plus 1. That's it. That's it. Now, what we can say is that this thing we can do on any one of the array, right? We can fix the partition inside array A and do the things with respect to A. Or the same thing can be done with respect to B also, right? The property that I said that if you know how many elements are there in A, you can calculate how many elements are there in B. Vice versa can also happen. If you know how many elements are there in B, you can calculate how many elements are there in array A. So my point is, we should do binary search on the array which is smaller in size. If let's say A is smaller in size, we should move the partition inside array. Otherwise, we can move the partition inside array B if B is smaller in size. Because the complexity of the solution, if you see the complexity of the solution, you are just doing binary search on A. So if the length of array A is M, the complexity will be log M. But if you just put a check, that if M is greater than N, that means A is greater than B, do binary search on B as it is smaller. So what you can do, you can say return median of two sorted arrays B comma, that is instead of A you pass B and instead of B you pass A. So if you will call this function call, then you will start doing binary search based on B instead of A. And if A is already lesser than B, then this if check will be avoided. What will be the time complexity? Due to this, the time complexity will be order of minimum of log M comma log M. So whatever is the shorter length array, you are going to do binary search just on that. So from M plus N log M plus N, we reduced our solution to M plus N, and now we reduced our solution to minimum of log M log N. And this is how you are going to get median of two sorted arrays at last. If you have never returned from between, then we are going to return -1 from here. And I believe there is some okay, we should not do return -1 here, we should do it here. And that's it. Let's try to run our code. We'll say console.log median of two sorted arrays. Let's say 7, 12, 14, 15 is the first array. And let's say 1, 2, 3, 4, 9, 11 is the second array. If you run it, the answer is 8. And that's correct. If you make any changes in the array, it will accommodate everything accordingly. And this is how we can write the code for calculating median of two sorted arrays in extremely efficient fashion using binary search. So let's just first of all understand that what the problem demands, right? So you are given a set of integers between -3 into 10 raised to the power 4. Let me check, it is 4 only. Yes, up till plus 3 into 10 raised to the power 4, both inclusive. Okay, both inclusive. What you have to find the number of 6 tuples. What is a 6 tuple? 6 tuple is a tuple with 6 elements, or let's say a set of 6 elements. A, B, C, D, E, F, such that A into B plus C divided by D minus E becomes equals to F. Like for the given 6 tuple that you have found, this equation should hold true for D not equal to 0, right? D should never be equal to 0, and for the remaining set of values, this equation should satisfy. You have to count how many 6 tuples are there, right? So for example, let's say you have an array 2 comma 3, right? So we can even repeat the elements in the tuple that we have to find, right? So for this, the answer should be 4. I can show you one tuple that you can make, and similar to that, you can find 3 more. So you can see 2 into 2 becomes 4 plus 2 by 2. This is 2 into 4, 2 plus 3. Sorry, 2 into 2 is 4 plus 2, 6. 6 by 2 is 3, or let's do one thing, let's make it 3. This becomes 8 minus 8 by 2 is 4. 4 minus 2 is equals to 2. So if you keep the value of A is equals to 3, B is equals to 2, C is equals to 2, D is equals to 2, E is equals to 2, and then F is equals to 2, then for this set 3, 2, 2, 2, 2, 2, right? For this set, this equation holds true, and we have to find like count of the number of such sets. We don't have to print the sets or print the tuples. We have to find the number of such tuples. This is something that we have to figure out. Okay, cool. So how can we solve the problem? Let's first of all discuss the brute force way. In the brute force solution, we can try to generate all possible sets of size 6, or we can say 6 tuples, and then among all of them filter out the ones that follow the equation. Okay, so in the brute force, because you have to find 6 tuples, so the brute force solution will say that try to find out all the possible 6 tuples. Among those 6 tuples, just calculate out that how many of them are actually following this equation. Okay, as a constraint for the problem, you can assume that the number of integers in the array can be as big as 10 raised to the power 2. Okay, there can be 100 integers. So if you want to find, or if you want to code this brute force solution, then how can you find all the possible 6 tuples? So if you want to find how to if you want to find the logic of how to calculate all the 6 tuples, you need to reevaluate or recall the logic in which we used to calculate all the possible pairs. Just like how we calculate all the possible pairs, similar to that, we can calculate all the possible triplets, then quadruples, and so on and so forth. So what we can say is, for a equals to 0, a less than n, a plus plus. Then for b equals to 0, b less than n, b plus plus. For c equals to 0, c less than n, c plus plus. For d equals to 0, d less than n, d plus plus. And we can put a condition that if a of d is equals to 0, we can continue, because we don't want to get a d value, like 0 value for it. And then for e equals to 0, e less than n, E plus plus. Then for f is equals to 0, f less than n, f plus plus. And then we can check that if a of like ARR of A into ARR of B plus ARR of C divided by ARR of D minus ARR of E is equals to ARR of F, then these indexes are going to give you one possible set of sextuples. Then you can prepare a count variable and then increment the count. But if you will carefully analyze, this is a nested loop of 6. So the complexity is going to be order of n raised to the power 6. And this is going to give you time limit exceeded because the length of the array is at max 10 raised to the power 2. This is going to be extremely huge. And why we are having a loop like this? Because this index A is going to denote what all possible options we have for putting A. We have n options, right? Then for all such A's, we have n more options to get B, because B can be any such number, right? Similar to C, then D, then E. That's why we are going to nest it. If you would have if you would have required to just find the pairs, we would have just gone with 2 nested loops. For triplets, just 3 nested loops, right? So when we have to find these sets of particular length, then nested loops works fine for us. But having a nested loop of order 6 is going to be extremely huge, because 10 raised to the power 2 whole raised to the power 6 is going to be extremely huge. We have to somehow figure out something so that the overall number of operations is at max 10 raised to the power 8. This is something that we have to figure out. So we need to find an optimal, or I would say optimized solution for the given problem. So now let's just see an optimized approach, like how can we optimize our brute force solution. This is going to be an interesting one, right? Okay, so just give me a second. Okay, so what we can say is that if let's say you are given an equation like A into B plus C by D minus E is equals to F. You can say A into B plus C is equals to F plus E into D. Right? We can modify this equation like this, where D is not equal to 0. Now, instead of creating a set like having a nested loop of order 6, what we can do is A, B, C define a triplet, and D, E, F define one more triplet. So we need to find that if we can generate all possible triplets and all possible triplets here, then for any 2 triplets, how many pair of triplets, like you can say a pair of triplets, how many pair of triplets are there that satisfy this equation? Now you might be thinking that how does that even help? In order to generate all the triplets, you will only need 10 raised to the power 3, sorry, you'll only need n cube time, right? If you just want to generate all the possible triplets, you can just say for A equals to 0, A less than n, A plus plus. For B equals to 0, B less than n, B plus plus. And for C equals to 0, C less than n, C plus plus. And that's it. This is how you will be able to get all the possible triplets. Now let's say you have all the possible triplets. Then what you can do is you can store the value of all the possible triplets based on this equation and based on this equation. So you can prepare 2 arrays, let's say M and N. In the array M, all the triplets you will generate from here, right? You will store the value as ARR of A into ARR of B plus ARR of C. You can store this value inside M dot push this, and similarly you can say N dot push ARR of like you can have a separate triple loop like this. So for D equals to 0, D less than N, D plus plus. Then you can say if ARR of D is equals to 0, then continue. And then you can say for F is equals to 0, F less than N, F plus plus. For E equals to 0, E less than N, E plus plus. You will say N dot push. This is what? F plus E, ARR of F plus ARR of E into ARR of D. Okay. You can just push it right there.
Okay, cool. So now you have both the arrays. In this array, you are storing the value of all the triplets that is given this equation, and in this array you are having all the triplets this where you are having this equation. Now, how much time you will take in order to generate both of these arrays? You will take order of n cube time. Order of n cube time for all these triplets plus order of n cube time for all these triplets. This will be order of n cube plus n cube, order of n cube. Now you have these two arrays with you. Now the overall problem boils down to the fact that for every element in array M, how many occurrences of that element is present in N? Why? Because any element in M denotes a set of triplet which was given this equation and generated a value. And here any value denotes that a set of triplet which was given this value. So if let's say for any element x in M, you are able to find that how many occurrences of x are there in N. We can say then all of those triplets are having same value. Can I say that? So let's just take a quick example. So let's see. So let's say you have 2 comma 3, right? Or maybe we can start even writing the code for it, and then with the code we can generate all the values. So we can say number of 6 tuples count. We can write a function count. We'll get an array, right? We'll say that let's create a new array M and a new array N, and then we can say let I equals to 0, sorry, a equals to 0, a less than arr dot length, a plus plus, for let b equals to 0, b less or let's okay, b equals to 0, b less than arr dot length, b plus plus, for let c equals to 0, c less than arr dot length, c plus plus, and we can say m dot push arr of a into arr of b plus arr of c. Okay, so let me check the equation. Yes, so let's bind it inside a parenthesis, and this should be good. Now similarly we can have let's say for d equals to 0, d less than arr dot length, d plus plus, we can say if arr of d is equals to 0, we continue. Otherwise we'll say for let e is equals to 0, e less than arr dot length, e plus plus, and then we write for f is equals to 0, f less than arr dot length, f plus plus. Okay, and then we can say n dot push, this is going to be arr of f plus arr of e into arr of d. Okay, let's say console.log m comma n. Let's say console.log m comma n. Let's try to call this function count with an array 2 comma 3. So if we try to run it, okay, this should be arr. Okay, now you can see all the possible triplets, right, that you were able to get was 6, 7, 8, 9, 8, 9, 11, 12, and then 8, 10, 10, 12, 12, 15, 15, 18. Okay, now I'm saying let's just even also sort both of them. Let's just sort both of them also. So we'll say m dot sort. I'll tell you why we are sorting. Okay, now if you print them in the sorted form, you'll get this. Okay, so let me just quickly write both of them. So we have 6, 7, 8, 8, 9, 9, 11, 12, and otherwise we have other array, we have 8, 10, 10, 12, 12, 15, 18. This is mn.
Okay, so now if you will see, now this whole array M is just values of some triplets. This whole value N is just value of some triplets, such that M is following this equation, N is following this equation. And for both of the set of triplets to be equal, their values should be equal. So we'll say how many occurrences of 6 is here? No such occurrence. How many occurrences of 7 are here? No occurrence. How many occurrence of 8? There is one occurrence of 8. How many occurrence of 8? There is one more occurrence of 8. How many occurrences of 9? Nothing. How many occurrences of 11? Nothing. How many occurrences of 12? There are 2 occurrences of 12. So we can say there were total 4 combinations that we were able to make. And if you will carefully see, like for the value 2 comma 3, for the array 2 comma 3, the answer should be 4 only. And this is only because this 8 is getting formed by some set of triplets. This 8 is formed by some set of triplets, and both of them are equal. That's how A into B plus C becomes equal to E plus F into D, right? That's what we have to do. So all we need to do is, for each entry in M, we need to find how many occurrences of all those entries is present in N. Now how can we find it? Because we have sorted both of the arrays, then for each entry we can search for its entry. And in order to search for the entry, we can use binary search because the array is sorted. So we will be able to apply the property of binary search, right? Now we have to find all the occurrences. So let's say for 12, we need to find the first index where 12 is present, and we need to find the last index where 12 is present. So for doing that, we can use lower bound and upper bound. Lower bound will tell you the first index which is greater than or equal to 12. Upper bound will tell you the first index greater than 12. So let's say this index is j, this index is I. In your answer, you will add j minus I, because these many, I would say, occurrences you were able to find. And that should be it, right? How can we code lower bound and upper bound? We have already discussed in the previous set of videos, so you guys can like refer that, right? So we are going to implement our solution. So what we can do is we can just quickly get lower bound and upper bound. So let me grab a lower bound from here. And let's grab a upper bound also. Okay, so we got lower bound and upper bound. Okay. Now, let's say we'll iterate over M. Let's prepare an answer is equals to 0. We'll say for let, we'll have a for loop for let I equals to 0. And this is going to be on M, I plus plus. Then for your current element is M of I, you will say that let lower bound is equals to lower bound on N comma element, upper bound is equals to upper bound N comma element. Okay, if you are not able to find the element, right? So let's see, if at any point of time any one of them becomes -1, if lower bound is -1 or upper bound is -1, we are going to continue. Otherwise, in my answer, we are going to add upper bound minus lower bound. Okay, and at last we are going to return answer. So if we try to do console.log here, so we are getting the answer as 4. And if we try any other test case, let's say 5, 7, 10. For this, the answer should be 10. 5, 7, 10. The answer should be 10. And we are getting the answer as 10. So our solution is working fine. And if you will see the complexity of the solution, here you have an n cube loop, here you have an n cube loop. Then you will be having n cube entries. So this will be n cube log of n cube, which is n cube log n. And then you are having similarly an iteration on n cube length, with every time having you are having a binary search of log n cube, which is log n only.
So your overall complexity becomes, in terms of time, it becomes order of n cube log n, and in terms of space, it becomes order of n cube, because you are having two arrays in which you have stored both of the I would say, like in both of the arrays you have stored all possible triplets which are following the corresponding equations, and that's it. After that you just sorted it, and for each index, for each element in M, you're trying to find the occurrences inside N using binary search, lower bound and upper bound functions. So I hope the overall logic for calculating the number of 6 tuples is clear to everyone. We are going to meet in the next set of videos where we are going to discuss some more problems on binary search. That being said, let's just wrap this video here. We are going to meet soon in the next set of videos. Till then, take care guys. Bye bye and thank you. Let's say that this is the problem statement I'm going to write. The next lecture in a high school requires two topics to be discussed. Requires two topics to be discussed. Okay. The ith topic is interesting by AI units for the teacher. So this AI represents that by what quantity the topic is interesting for the teacher, and by BI units for the students. BI units for the students. The pair of topics I and J, such that I is less than J, is called good, if AI plus BI, if AI plus AJ is greater than BI plus BJ, right? Your task is to find the number of good pairs of topics, So let me explain the problem to you guys. So you will be given like a bunch of topics, right? A topic is considered interesting for both teacher and students. By what unit the topic is interesting for the teacher is defined by AI, and by what unit the topic is interesting for, I would say, the student is defined by BJ. What we have to figure out is we will be given a pair of topics, I and J, right? And let's say this pair of topic will be called as good, if it will be called as a good pair, if the sum of AI and AJ is greater than the sum of BI and BJ. That means the pair of topics are more interesting for the teacher cumulatively. What we need to find is we need to find how many such good pair of topic exist. Like if let's say there are n topics and there can be approximately n square pairs, so how many good pairs are there is something that we have to figure out. So I would highly recommend you guys to pause the video here and think about the solution, and if you have given a good thought, then maybe we can start the discussion on the problem. So let's just see an example for the corresponding problem. So let's say that we are given 5 topics. So let's say n is equals to 5, and the units by which it is interesting for teacher and students is given like this. Let's say the first topic is interesting by 4 units for the teacher and 4 units for the student. Second one is 8 units for teacher and 5 units for students. Then third one is 2 units for teacher and 4 units for student. Fourth one is 6 units for teacher and 1 unit for students. And then you have 2 units for teacher and 3 units for students. So these are like 5 topics that have been given to you, right?
The answer for this test case, is going to be 7. That is, there are going to be 7 pair of topics such that you can have good, like all those pairs are going to be good. Let's see what are those pairs. So you can see that 4, 8, 4 plus 8 is greater than 4 plus 5. So this is the first pair. Then you can see 4, like the first one, and the fourth one, like 4 plus 6 is greater than 4 plus 1. So this is the second pair. Then you can see these two, 8 plus 2 is going to be greater than 5 plus 4. So this is the third one. Then this one and this one, 8 plus 6 is going to be greater than 5 plus 1. This is the fourth pair. Then this one and this one, 8 plus 2 is going to be greater than 5 plus 3. This is the fifth pair. Then these two, 2 plus 6 is going to be greater than 4 plus 1. This is the sixth pair. And these two, 6 plus 2 is going to be greater than 1 plus 3. This is the seventh pair. So these are the 7 pair of topics such that AI, like the topic is more interesting for the teacher, so that AI plus AJ is greater than BI plus BJ. This is for this test case. If you write one more test case, like n is equals to 4 this time, the A and B array is something like this. 1, 1 for both. Then you have 3, 3. Then you have 2, 2. And then you have 4, 4. So for this test case, the answer is going to be 0. That is, there is no pair of topics such that the topic is more interesting for the student, because you can see every time AI plus AJ will be equal to BI plus BJ for this test case. Okay. If you talk about constraints, if you have to see the constraints, then we can assume that n can be, like the number of topics will be as big as 2 into 10 raised to 5, right? And any value A of I and B of I, both of them will be as big as 10 raised to the power 9. Okay. These will be the constraints that we have to consider. So let's see how we can solve this question. So in order to solve this question, we can take a brute force. We can take a brute force approach. What will be the brute force approach? In the brute force approach, we can try to form all possible pairs. We can try to form all possible pairs of topics, and then filter out the pairs which are more interesting for the teacher. That is, AI plus AJ will be greater than BI plus BJ. Okay, we can do this. So let's see how we can construct all the possible pairs. So if let's say you have an array of some elements A, B, C, D, E, you have to form all possible pairs. So pairs will be, A will be paired with all the other numbers, then B will be paired with all the other numbers, C will be paired with all other numbers, and so on and so forth. So what we can say is, for I equals to 0, I less than n, I plus plus. This I is going to denote first element of the pair. And then for this first element of the pair, J is going to start with I plus 1. J will be less than n, J plus plus. J will denote second element of the pair. Right. And then if you write print A of I, comma A of J, this will print all the possible pairs. So we can use this strategy in order to form all the possible pairs and then filter out from those that which of them are more interesting for the teacher. If you will see the two loops, that these two are nested loops, and in the worst case, the time complexity is going to be order of n square. And if n is 10 raised to the power 5, 2 into 10 raised to the power 5, then n square is extremely huge. So we need to devise a strategy so that we can optimize the solution. So let's just see how we can optimize the solution, right? let's say that you have to figure out for how many pairs of topics a of I plus a of j is greater than b of I plus b of j, right? So if we try to modify them a bit, this becomes ai minus bi is greater than bj minus aj, right? Which implies to ai minus bi is less than aj minus bj, right? So technically, all we have to do is, let's cut out this test case, cut this out, copy, paste. If from this array, if we try to make a new array such that c of I is equals to ai minus bi, because we can imply it as c of I is less than c of j, right? So we can say, just a second, this should be, or we can write it as like this also, like instead of doing it like this, we can say this is greater than minus of aj minus bj, right? Same thing, which implies to ci is greater than minus of cj. So if ci is equals to ai minus bi, so let's create the ci array. So this is 0, this is 3, this is minus 2, this is 5, this is minus 1. Okay, so now technically we have to figure out in the array C how many pairs are there such that if there is a pair I where I is less than j, the value at I should be greater than negative of the j. So let's see, for 0, after 0 how many values are there such that it is 0 is greater than negative of that value. So we can see 0 is greater than minus 3, right? 0 is greater than minus 5, right? So 2 pairs are coming from here, so 2 plus. Now for 3 is greater than minus of minus 2, that is plus 2, and 3 is greater than minus of minus plus, that is plus 1, so 2 more coming from here. Then minus 2 is greater than minus 5, so 1 coming from here, and 5 is greater than minus of minus 1, that is 1, so 1 more coming from here. And let's see, are we missing anything? So for 0 we got this, we got this, right? 2 for zeros, and for 3 we got this as 2. Okay, and 3 is greater than this also, right? 3 is greater than minus of minus 2, that is plus 2. 3 is greater than minus 5, and 3 is greater than 1 also. This should be 3. This should be 3. This totals out to 7, right? So technically, if we modify this array to this C array, in the C array we have to calculate how many pairs are there such that for I less than j, C of I is greater than negative of Cij. That is something that we have to figure out. So, and we don't care about the positions of the element, we just have to count them. So if we just sort this array, if we just sort this C array, this will become minus 2, minus 1, 0, 3, 5, right? Now on this array, if we take any element, let's say 3, right? Or let's take minus 2. So for minus 2, we'll try to figure out that after minus 2, how many elements are there such that they follow this property, right? Let's try to do the dry run again for the sorted array. So for minus 2 is going to be greater than minus 3 and minus 5. So 2 plus minus 1 is going to be greater than again minus 3 and minus 5. So 2 more. And 0 is going to be greater than minus 3 and minus 5. So 2 more. And 3 is going to be greater than minus 5. So 1 more. So this totals out to 7. So what we can say is that for any element, we'll just loop over every element. And we will say that in this remaining array, how many elements are there such that the current element C of I is greater than negative of those elements, right? We have to find this. And we already know that for binary search, we have already discussed solutions like lower bound, right? We have already discussed solutions like lower bound. I'll explain a bit of lower bound again if you guys want. But what lower bound says that for any element, we have to find the first index which is greater than or equal to that element, right? So let's say for if you want to find lower bound of x in an array, we've tried to find the first index which is greater than or equal to x. So here we have to find the first index which is greater than, for which let's say the first index which is greater than negative of cj. So if I consider this element as j, now we can avoid this property. If we consider this element as index j, then we have to find how many elements are there which are greater than negative of this element, right? We can do it like this. Or if we consider this as c of I, we have to consider how many elements after it are there for which the negative of these are greater. So we can modify it. We can say c of I is minus of c of I is less than c of j. If you visualize it like this, then it would be a bit more simpler. That is, we have to find all those elements which are greater than minus of ci. If you consider this as index I, like both of the ways works. If you consider it at index j, then you have to find this. Or you consider this as index I, then after this you have to find all those elements, because we considered in that I is less than j. We have to find all those elements which are greater than negative of this element. So if you have to find the lower bound, if you will be able to find the lower bound will help you to find something that is greater than or equal to the negative of this. If you have to just find the greater than of it, then you can just consider plus one index, right? Or you can find even upper bound. You can even find upper bound. Upper bound also helps you if you have a function of upper bound. Then upper bound of x is going to help you to find the first index which is greater than x, right? And both lower bound or upper bound, whatever you use, both of them can be implemented using binary search. Both of them can be implemented using binary search, right? Okay. So let's just try to figure out with a very quick explanation that how upper bound and lower bound, any one of them which we can use, works. Upper bound. What the problem says is that given an array of integers which is sorted, and an element x right, find the index of the first value greater than x, right? So let's say that you have got something like 1 2 3 3 3 5 6. Let's say this is the given sorted array to you, and let's say the value of x is equals to 2. Now what is the first value which is just greater than 2? It is 3, right? This 3 is the first value which is just greater than 2. And if we see the indexes, so for x is equals to 2, the answer should be 2, that is the index 2, because at index 2 we have a value 3 which is just greater than x. If let's say we have a value like 3, then for x is equals to 3, the answer will be 5, because 5 is the first value greater than x, right? And the index is also 5, so for this also the answer should be 5, right? This property, this value, like the first value greater than x, is sometimes also called as the upper bound. So we have to see that how can we solve the problem of upper bound. Okay, so if we go for the brute force approach, then the brute force approach will be to apply linear search on the array and check every element one by one. The first element we find which is greater than x, we return the index for it. Okay, right. So we are just going to iterate one by one, and the first value which is greater than x, we'll just going to return the index for it. The time complexity for this approach is of course going to be order of n, because let's say x is the biggest value of your array, then there will be no upper bound, right? In that case also you are going to iterate over the whole array and still not find anything. So the time complexity is going to be order of n. How can we optimize? We can optimize the problem using binary search, or I should say solution. We can optimize the solution using binary search, right? Because of the fact that we have a monotonically increasing sequence, like the array, let's just cut paste the array. Okay, because of the fact that we have an increasing sequence which is monotonically increasing, right? We can also again do the same thing. We can try to manipulate this array in a bunch of trues and false. So if I write this array like this, let's say x is equals to 3, and let's say I write the array like this: true, 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 false, false, or just opposite of it, like false, 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 true, true. Anything we can write. Let's go with the latter one: false, 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 true, true. Okay, now if I try to think an array in these terms, then again we have to find the first true. Again we have to find the first true, right? This is something that we can do. So again, if this is the search space in which we have to find the first element greater than x, then we can say that we'll be able to divide our search space into two parts, and both of the parts will be having a property based on which we can distinguish the parts, and the property again is going to be same. That is, one part is only going to have either true or either false, and the other part is going to have a mix of them. Or in simple words, we can say that one part, if let's say you increase it to like 7, 8, 9, 10 and everything, if your mid comes somewhere here, then the right part is only going to have all the greater elements, and the left part is going to have some greater, some lesser elements. Or your mid comes somewhere here, so on the left part we'll be always having the lesser elements, on the right side we'll be having mixed elements. So this property is again going to be there. That is, we can divide the search space because every time we will get one part as mix values and other part having just greater or just smaller values, right? So we can again apply binary search here. So let's see how can we do this. So if we try to paste the same array, we'll get our mid. Initially start is here, end is here. We'll try to get the mid. Mid is 6 plus 0 by 2, that is 3. So mid is here. Now you can see that the value that we had x was for 3, for which we want to find the upper bound. Now the value of 3 is equal to 3. That means everything to the left of 3 is either equal to x or lesser than x, because this is a sorted sequence. Everything to the left of this 3 is either equal to 3 or lesser than 3, and we want to find a greater value. That means if on the mid we find a value which is equal to x or lesser than x, then that means that we have to find our answer on the right side, and this can never be our possible answer. So this time what we are going to do, we are going to do start is equals to mid plus 1. Start comes here. Okay, now we'll again try to calculate the mid. This time start is at 4, end is at 6. 6 plus 4 by 2 is 10, right? 6 plus 4 by 2 is 10 by 2, which is 5. Mid is 5. This time mid is 5. Now we'll again check. Is 5 less than or equal to x? No. 5 is greater than x. Now there can be a case that this 5 can be a possible answer, but there can be a better answer than this 5, right? So let's just try to increase our example a bit. So let's say, let's not remove this. Let's say this is also 5. Okay, let's say this is also 5. Now we can say that our mid is at index 5, which is having a value 5. This value 5 is greater than x. The moment we find a value which is greater than x, it can be our possible answer. So inside our answer, I'm going to store the index, which is 5. And the thing is, this can be our possible answer. Whether this is our final answer or not, we are not sure, because everything to the right of this element is greater than x. And we want to find the first element greater than x. So if everything to the right of this is greater than x, then definitely on the left of it, there are mixed elements. That means some elements can be greater than x, which are on the left side. So what we have to do is we have to converge on the left. We do no point of going to the right, because every element is already greater than x. We want to find the first element greater than x, because instead of the rightwards element, this is even a better answer. So now we'll do end is equals to mid minus 1. So this time end comes here. Now start and end are on the same point. 4 plus 4 by 2 is again 4. Mid is 4. This value is again greater than x, right? We will say that this is a better answer for us because the index is lesser. So we'll say 4. And then we'll try to converge that maybe some better answer is there. And we'll do end is equals to mid minus 1. Now start and end are across each other. Things are done. So let me write this whole algorithm that if the middle element is less than or equal to x, there is no point of searching the answer on left side, on left part, because everything on left will be also less than x, right? That means we should jump to the right part. How do we jump to the right part? We'll say start is equals to mid plus 1. Otherwise, if mid element is greater than x, then this can be our potential answer. This can be our potential answer, right? We can store this index in answer and try to find a better answer. For it, we should jump to left part, because on right we only have greater than x elements, right? To the right of it we only have greater than x elements, and the current middle element is also greater than x, so it is definitely a better option than all the elements to the right, because we want to find the first element greater than x. And that's it. That's all we have to do. If you want to jump on the left, you know how do we do it. We do end is equals to mid minus 1. So based on the logic of upper bound, this is the implementation that we can do. We have already discussed a similar implementation before, so you can even check that out. But the overall explanation is going to be same. That we have just made a few modification for this upper bound. That instead of starting from 0th index, we are going to start with a particular element, because for finding the pair of topic, we have to always look forward toward it, and then every time you are just going to check if the element is less than or equal to greater than or equal to the element at the middle, then definitely this is not our answer. We have to look a bit forward to it. Otherwise, if we found a value, then we can find a better value on the left side, so we'll move on to the left side, but we will add it as a candidate answer. So we can use this, and we can start the implementation for the pair of topics. We can use this upper bound function and then implement our, I would say, pair of topics by using this upper bound function as a subroutine.
So now we have our upper bound with us. Let's just quickly change the name of the file to pair of topics. Right. Second, let's rename it pair of topics. Okay. And then instead of the basic upper bound, what we can do is we can also pass an element as st, which is going to denote start, that after what index you have to, like this upper bound works on the whole array. We can just start with any particular index, right? And then what we can do is for our input, let's say we'll be given two arrays. So let a is equals to, let's say 4 8 2 6 2, and let b is equals to 4 5 4 1 3, right? What we'll say is let's calculate a new array. So for let I equals to 0, I less than a dot length I plus plus, we'll calculate a new array. Let's say let c empty array, and we can say c dot push a of I minus b of I, and then we can sort the array c. So we'll say c dot sort, we'll pass a custom comparator a comma b, which returns a minus b, and then we can say let's see, we'll say for let I equals to 0, I less than c dot length I plus plus. We'll go to every element, and we don't even need to go to the last element. So c dot length minus 1. Let's prepare an answer. Let answer is equals to 0, and then for each element we'll try to find the upper bound. Okay, so let upper bound is equals to, let's call upper bound with the array c. The element for which we have to find is going to be negative of the current element, so minus of c at I, and the start index is going to be I plus 1. Okay, let's see what is the upper bound giving us. Let's try to see what is the upper bound giving us. So if we try to run it, let's clear the console and run it again. Okay, so for the 0th index, the upper bound is giving us 3. So if you see it here, 0 1 2 3, right? And that's correct. How many elements are greater than minus of minus 2? 2 elements are there. So I believe this should be good. So in our answer we should add c dot length minus upper bound. Okay, and if we try to do console.log answer, okay, let's check. This should be plus equal to, and we are getting the correct answer 7. Let's try the other test case. 1 3 2 4, copy paste, let's run it. Okay, for this the answer is coming as 15. This should not be the case. Let's see what is there in C. So console.log C. Okay, because every array is 0, so we have not handled that case in our upper bound, right? So at any point of time when the upper bound is not able to find like the element, then we should do this. If answer is equals to arr dot length, let's say we are going to return 0, otherwise we are going to return answer. Okay, or let's say let's not hamper the upper bound, let's handle it here only. So if the upper bound is equals to, let's see what first of all what the upper bound is there. So console.log the upper bound. So you can see every time the upper bound is coming as -1, right? So let's say if upper bound is equals to -1, we are going to say we are going to continue. Okay, so let's see. If you run, you can see the answer is coming as 0. So this can be a corner case that we can touch up, and things are good.
So you can see we successfully implemented the solution for the upper bound as well as the solution for the pair of topics. You can just return this answer and that should be good. What's the time complexity? If you see, you are sorting this array here. So this sorting will take order of n log n. And then on the array C, every time you're calling binary search. So on n length array, you're calling log n calls. So final complexity is order of n log n plus n log n is order of n log n. This will be the time complexity. Right. So I hope the logic for the overall problem of pair of topics is clear to everyone. We are going to meet soon in the next set of videos where we'll be discussing more problems on binary search. That being said, let's just wrap this video here. Till then, take care guys. Bye-bye and thank you. You will be given a sequence of n given a sequence of n numbers, right? Given a sequence of n numbers where n is less than or equal to, let's say, 34, right? How many subsets of the sequence have a sum between two numbers a and b? Like how many subsets are going to be there of this set of number n such that the sum of the subset is between the range a to b, both inclusive, right? So for example, let's say you have something like a is equals to -1, b is equals to let's say 2. Okay, and let's say you have a sequence of n numbers, n is equals to 3, and the sequence is 1 - 2 3. So for this test case, the answer should be equals to 5. Why the answer should be 5? Because how many subsets are there? There will be an I would say one empty subset which is in the range -1 to 2, right? Because the sum is 0. Then you have just a subset of 1 which is also in this range. Then you have a subset 1 comma -2 that is also inside this range because 1 - 2 is -1. Then you have a subset -2 comma 3 that is also in this range because -2 plus 3 is 1. And then at last you have a subset 1 comma -2 comma 3 that is 4 - 2 is 2, that is also in this range. So there are like 5 subsets which are in the range, like whose sum is in the range a to b. So the answer is going to be 5. So this is what we have to calculate, right? Okay. So how can we solve the problem? So what we can see here is that if we try to go for a brute force, solution, then we can generate all possible subsets and then filter out the subsets having sum in the range a to b. Okay, having subsets in the range a to b. Okay, so what we can do here is, if we try to generate all possible subsets and n is at max to 34, then for a set of size n, the number of subsets are 2 raised to the power n. So 2 raised to the power 34 is going to be approximately 10 raised to the power 9 and something a bit more than 10 raised to the power 9. So this solution is going to give you time limit exceeded because you will be generating all the subsets. For those subsets, you will be getting the sum and then you will be checking if the sum is in the range a to b. This is going to be time limit exceeded. It is not the most optimal solution. So how can we optimize? Before we go to the optimization, I would recommend we should code this brute force solution, or at least we should code the part where we are generating all the possible subset, because this part is going to be used in the optimization as well. So let's just do it. So we need to figure out how to generate all possible subsets. How to generate all possible subsets. So let's say you have an array 1, 2, 3. The array is of length 3, so there are 2 raised to the power 3, that is 8 subsets. So in order to figure out the logic that how can we generate all possible subsets, there can be like two ways. One way is a recursive way, right, that we have already discussed in like previous set of modules. But there is one more iterative way also that we can implement here. So in order to understand any of such way, we have to understand the core logic behind subsets and like how this formula of 2 raised to the power n comes into the picture. So if you have a set of size n and you have to figure out all the possible subsets, then how do you generate it? On every element, you have a choice that whether the element can get added in the subset or that element can be avoided to get added in the subset. For example, in a subset, I have two choices for one, that we can add one in the subset and we cannot add. Same two choices for two, same two choices for three. So for example, if we add two, if we do not add one, if we add two and add three, so we get a subset 2, 3. If let's say we add 1 and add 3, but we do not add 2, so we get a subset 1, 3. So this is the logic that we do, that at every element, we have two choices, either to include it in the subset or avoid it. So due to this fact that on all the n elements you have two choices, so two choices here, two choices here, two choices here, this leads to 2 raised to the power 3. So if you have n elements, so 2 into 2 into 2 into 2 n times is going to be 2 raised to the power n. Okay. So having this property in mind, now let's say you have this array 1, 2, 3. How can you generate all the possible subsets? So what we can do is we can take the help of binary numbers, because all the decimal number that we represent can be represented in the form of binary numbers. So what I'm trying to say is that if we try to allocate all the possible binary numbers of size 3, for example 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, and so on, so like all the possible binary numbers, then every binary number represent a subset. How? If let's say 0 represent avoid and 1 represent consider, then if we have something like 0, 1, 0, then we say that this element we will avoid, this element we will consider, and this element we will avoid. So we get a subset 2. If you have 0, 0, 1, then both of these are going to get avoided and we are going to include 3. So subset we get is 3. If all of are 0, none of them are going to get included, so the empty subset. If all of them are 1, then all of them are going to get considered, and so on and so forth. So if you can generate all the possible binary numbers, then based on the binary digit on some ith position, you will be able to understand whether the ith element is included in the subset or not included in the subset. So what we can say is, let's say you have 1, 2, 3, because there are 3 elements, so subsets will range from, so total number of subsets will be 2 raised to the power 3. So we can say, let's say 0, 1, 2, 3, 4, 5, 6, 7. So there will be like 8 possibilities. Now if you write binary number for all of these, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, sorry, 1, 1, 0, 1, 1. These are the 8 binary numbers. If you pick any one, 0, 0 means empty set, 0, 0, 0 means 0, 0, 1 means just 3, 0, 1, 0 means just 2, 0, 1, 1 means 2, 3, 1, 0, 0 means just 1, 1, 0, 1 means 1, 3, 1, 1, 0 means 1, 2, and 1, 1, 1 means 1, 2, 3. So we have all the possible subsets, right? So what we can do is we can iterate from 0 to 2 raised to the power n minus 1. And then for each number that you have got, each I that you have got, you can convert this I to the binary format. And inside the binary of that number, what you can do is, if the binary at a position x is 0, you are not going to include the xth element, otherwise you are going to include the xth element. That's it that you have to do. Now how can you convert your element into binary, right? So you don't have to actually convert them. right? You don't need to like convert 1 into binary of 1. What you can do is you can just check that at any xth place we don't need to generate the binary numbers, the binary from decimal. We can use the decimal and check if at any xth position the binary bit is set or not, right? So we can very easily detect it whether the binary bit at any xth index is set or not. For example, let's say you have 5. If you do 5 and 1, so what is 5? 101, 1 is 001 and is 001. 5 and 1 denotes that on the last, I would say, place, you have a set bit because everything else is 0. Only this is 1. If you did AND with 1 only, then only the answer will be 1, right? Now let's say if you AND 101 with 010, then the answer is 000. That denotes that because rest everything was 0, only this index was 1 and the answer is 0. This is due to the fact that inside 5 this index was 0. Then let's say you have 100, then it will detect that on this position whether you have 1 or not. So if you have a 1, it will be 100, right? This is something that maybe we can try to do. This is something that we can try to do, right? So we will say that if we want to detect that for any number, I would say m, if any ith position is having or xth position is having a set bit or not, you can just say m and 1 left shift x. What is 1 left shift x? If you are having initially 001 and you do left shift 1, this becomes 010. If you did left shift 2, this becomes 100, right? So in the left shift, what happens is you replace the most significant bit, you truncate the most significant bit and you add a 0 at the least significant bit, right? I hope logic of how bitwise operator works is clear to everyone. So let's just try to use this logic. First of all, let's just iterate here. Then I'll show you how you can check this logic working, right? So we can say subsums.js. I'll write a function subsets. You are given an array. Okay, let's say let n is equals to arr.length and total number of subsets. So we'll say let count of subsets is equals to 2 raised per n. How can we calculate 2 raised per n? If we do 1 left shift n, 1 left shift n is equivalent to 2 raised to the power n. Let me show you how. So let's say you have 1, binary of 1 is 0001, let's say. Now if you do 1 left shift 1, this becomes 0010. This is 2. If you do 1 left shift 2, this becomes 0100. This is 4, which is 2 raised to the power 2. If you do 1 left shift 3, this is 1000, which is 8, which is 2 raised to the power 3, right? So every time with whatever position you are shifting, you are getting a power of 2. Okay, so let's just quickly check. So here we will get count of subset, that is 2 raised to the power n. So we can write 1 left shift n is equals to 2 raised to the power n. Okay, cool. Now we can say for let I equals to 0, I less than n, let's say I less than count of subsets, right? And let's see, or let's say let's keep it number. Let's not keep it I, let's keep it number. Okay, so we are going to go from 0 to 2 raised to the power n minus 1. Now for every number we have to check, that what bits are set, what bits are not set. So we'll say let sum is equals to, or let's say let arr is equals to an empty, let's say let a is equals to an empty array, and then we can say that for let's see, Okay, so we can say that for let I is equals to 0, I less than, okay, so you have numbers around 32 bits, right? So let's see. Okay, so we can say, let's say we are going to go to 32 bits, right? So I less than 32, I plus plus. We will say that, and we don't even need to go to 32 bits. We should go to only the number of bits which is equal to the array dot length. So we'll say array dot length, and then we say that if the number and one left shift I, if this value is not equal to 0, we are going to say a dot push arr at I. Okay, so let's see. Yes, this should work. And at last we'll do console.log a. Let's see if we are able to get all the subsets or not. So we'll say subsets. We pass an array 1, 2, 3. So you can see we are able to generate all the possible subsets. You can see all the subsets are getting generated. So now instead of getting the subsets, we can even get their sum, and we'll say sum plus equal to arr at I. Right, and we can pass a and b. So we'll say if sum is greater than or equal to a and sum is less than or equal to b, we'll say count plus equal to 1. So we can keep a count. Let count is equals to 0. At last we can return count. So let's just try with the test case given in the problem. So we'll say 1 comma minus 2 comma 3. The value of a is minus 1, the value of b is 2. If you run it, let's do console.log. Okay, we are getting 5 as the answer and 5 is the expected output. But the only problem is that the time complexity here is 2 raised to the power 2, time is order of 2 raised to the power n, right? Where n is 34 at max, so this will give you TLE, time limit exceeded. Space complexity is order of 1. So this solution is going to give you time limit exceeded, but why I coded this solution is because a big part of this solution we can directly use in our optimization. So all we have to think is how can we optimize this problem, right? Okay, so let's just see that how can we optimize the solution. So we know that if n becomes as big as 34, like n is approximately around 34, then 2 raised to the power n is approximately 10 raised to the power 9. This is going to give you time limit exceeded. But let's say if n is approximately somewhere around 17, then 2 raised to the power n will be somewhere around 10 raised to the power 6, 5 to 10 raised to the power 6. This is kind of like a possible situation. Like this is something that is possible, right? That is computable in 1 second. So what I'm trying to say is divide your array into 2 parts, right? Divide your array into 2 parts. For each part, generate subsets separately. Like for example, you have an array of length 34. I'm asking you to divide your array into 2 parts. Each part will be of length 17, and then for each this small array, generate all possible subsets. Generate all possible subsets here. Generate all possible subsets here. So here you will get 10 raised to the power 6 subsets around and 10 raised to the power 6 subsets around here. So both of these are going to be computable, and if you generate like 10 raised per like if you take 10 raised per 6 operation to generate subsets of the first half of the array, and then 10 raised per 6 for the second half, it is approximately 10 raised per 6 only. So generating these two separately is going to be convenient for us. Okay. Now, having two different arrays whose subsets we already have, like, and instead of subsets, let's say generate subset sums. Like, we can just store the subset sum, because sum is something that we have to that we are expected to be concerned about. Now, having subset sums for these two separate arrays, how can we do something? So what we know is that for the whole array, or let's say for the subset sums, we can try to map this problem to the 6 tuple problem. In the 6 tuple problem also, we were having an array such of such big size as that n raised to the power, like generating all possible 6 tuples was not possible. So instead what we did was we tried to generate all possible triplets, right? And then for those two triplet sets, we put them in equations, and then got two arrays, and then tried to search the elements of one array in the other array. So similar thing we can do. What I'm trying to say is that, let's say you have an array M, and inside M you have subset sums of first half, and let's say you have an array N where you have subset sums of second half. When I say subset sums, then I mean that this sum that we are generating, right, this is sum of one subset, so all subset sums, right? And then what we can say is that if we pick an element X from M and an element Y from N, then X plus Y should be greater than or equal to A and less than equal to B. Can I say that? Right. I'm saying for the, let me repeat myself, like for the whole big array of size 34, all the possible subset generation is not possible because it will give you time limit exceeded. I am saying divide your array in 17 length in the worst case. Generate subset sums for first half separately. Generate subset sums for second half separately, because they will only be 10 raised per 6 entries. And store them in an array M and N. Then any element X inside M and any element Y inside N, if the sum of this element is in the range A to B, this is a valid answer, right? This is a subset which we can include, because this X is denoting a subset, this Y is denoting a subset, and if we do X plus Y, then we are actually just combining the both subsets. So that's why the sum got combined. That's all we have to do. And technically, if you see, then this equation leads to X should be greater than or equal to A minus Y, and X should be less than or equal to B minus Y. So what we can do here is, or let's say, let's do one thing. This should be A minus Y, right? Or let's say we'll do one thing. We'll say A minus X should be less than or equal to Y. This is something that we can do. And B minus, let's say, X should be greater than or equal to Y. Okay. This is something that we can do. So what are these two inequalities denoting? These inequalities are denoting that if, let's say, we have an element X from the M and we subtract it with A, so A minus X. So inside the array N, if we are able to find all such Y's which are greater than or equal to this, right, as well as we are able to find all such Y's which are less than or equal to this, then we can find all possible solutions, something like this, right? So if in the array n we can count all the elements which are less than or equal to y, and sorry, less than, let's say it like this, which are greater than or equal to, let's say, a minus x, and we can say less than or equal to b minus x. Then all those elements y, when combined with x, form a subset whose sum is between a to b. Now you might be thinking some subsets can also come from just m and just n, right, without like combining both of them. So that part also gets included, because here we'll be having an empty subset. An empty subset of n when combined with a filled subset of m makes a subset of m only, right? So we don't, like, this is a general logic only. You don't have to separately calculate that how many subsets are there whose sum is between a and b, because when you will be combining them, then there will be an empty subset whose sum will be 0. So 0 plus any element will be that element only. So that part we can. Now in order to find out that how many elements are greater than or equal to a minus x and less than or equal to b minus x, we can try to use the logic of upper bound and lower bound. Upper bound help us to find the first element which is greater than a particular element. So if we are able to find the first element greater than b minus x, before that all the elements will be less than or equal to b minus x. And if we are able to find, and if we use lower bound gives you the first element greater than or equal to that element. So if you are able to find lower bound of a minus x, so y is what? The first element which is equal to or greater than a minus x. So here you can apply lower bound and here you can apply upper bound, and you will be able to get your final answer, right? So now we have already discussed in the previous videos how we can implement upper bound and lower bound. So we are just going to quickly take that and we'll try to implement the solution. But before we implement the solution, what will be the time complexity? So here you can see 2 raised to the power n by 2. Order of 2 raised per n by 2 is getting implied here, plus this array is going to be of size 2 raised per n by 2. This array will be of size 2 raised per n by 2. So when we are doing binary search here, we have to first sort it. So 10 raised per 6 log of 10 raised per 6 will be less than 10 raised per 8, no issues. And then we'll apply binary search on size 10 raised per 6, that will also be less than it. So 10 raised per 6 plus 10 raised per 6 log 10 raised per 6 plus log 10 raised per 6 is less than or equal to 10 raised per 8. So this solution will work, right? So let's just try to quickly implement it. So I'll just quickly get our lower and upper bound. So this is an upper bound. And let's get a lower bound also. Okay, now we have lower bound and upper bound. Now we are generating this subset. So let's do one thing. So we'll be given this array, right? So this array is ARR. This is A and this is B. Okay, so let okay, and let's see, in this subset, instead of returning the count, what we are going to do, we are going to have a resultant array, and in that array I'm just going to push the sum. So let's dot push sum, and we are going to return the array. Okay, and just a second. Now from here, what we can do is we'll say const left is equals to arr dot subarray right. This is arr dot subarray, and this should be let's see, from the index 0 to arr dot length by 2, and let's say const right is equals to arr dot subarray from arr dot length. Let's print first of all left and right. Left and right, let's see what we are getting here. Let's say subarray is not a function. Let's check. Okay. Okay, instead of subarray, we can do slice. We can do slice in JavaScript. We can do slice. So let's slice it, right, and slice here as well. Okay, so we got this. Let's say, let's try different cases. So 1, 2, 3, 4. If you see, then you're getting 1, 2 here and 3, 4 here. If you do 5, then you're getting 1, 2 and 3, 4, 5. And let's say you just have 1, then you just have an empty and 1, right? So this is going to give you all possible subset, sorry, all possible, like it's going to divide your array into two parts. So you have now two arrays. Now what you can do is you can say const m is equals to subsets on left. Let's not pass a and b, we don't need it. Const n is equals to subsets of right. Now we can just sort both of them. So m dot sort a comma b with a minus b, and n dot sort a comma b with a minus b. And then we can say for let I equals to 0, I less than m dot length I plus plus. Right, now we are going to apply our logic. So in order to apply the logic, let's see, we have to find the lower and upper bound. So we'll say let lower bound is equals to lower bound, and we are going to pass the array n. The element will be m of I, right? And we don't have to pass m of I. This should be a minus m of I. So lower bound will be from there. We'll say let upper bound is equals to upper bound on end. It should be b minus n of I, right? And then in my answer, I'll say answer plus equal to upper bound minus lower bound, because everything in between is our answer. So let answer is equals to 0, and then we'll say console.log answer. Let's try to run it. So we're getting minus 3. Okay, let's do one thing. If upper bound is equals to minus 1, like we have a case of minus 1, right? And lower bound is equals to minus 1, we continue. If any one of them is not present, okay? Okay, we are getting 0. Let's see. Or let's do one thing. If upper bound is equals to minus 1, let's say we'll do upper bound is equals to n dot length. And if lower bound is equals to minus 1, you can say lower bound is equals to n dot length. We are getting 7. This should not be the 7. This case should not be 7. Let's see, what are we missing? Okay, so we have, these are the subsets and subset sums technically. So between -1 and 2, you can see 0 is there, and then you have 1. So 1 plus -2. Okay, let's see. Um, Shall do console.log a minus m of I, comma b minus m of I. Okay, we run it. So this is -1 and 2. Okay, so we need to find how many elements are greater than or equal to -1. So we have 0, 1 and 3. And then how many elements are, okay, let's see. This should be working. We are doing it on n, we are iterating on m. Makes sense. Let's see. Try to find upper bound for this. This should be b minus n of I. Let's say console.log this b minus m of I and lb ub. Okay, let's see. Let's remove this. So we are going to go to each element, and the current element m of I is 0. So a minus m of I becomes -1, b minus m of I becomes -2, because a and b are -1, 2. So -1, 0 is this. Sorry, -1 -0 this, and 2 -0 this. Okay, so you have to find that how many elements are between -1 to 2, right? And we have got 0. So how many elements are there which are between -1 to 2? So we can say these 3 elements are there. Okay, so we got the lower bound as 1, makes sense, and upper bound as 4. So 4 minus 1 is 3. We got 3 from here. Okay, then next element is 1. So -1 minus 1 is -2. 2 minus 1 is 1. So how many elements here are between -2 to 1? So we're going to find a lower bound for -2. So here we have a -2, and we want to find an upper bound of 1, right? I believe upper bound is not working fine. Lower bound, upper bound. Okay, yeah, my bad. So here technically upper bound was expecting a start. We should not have a start. This should be always 0. That's why it was returning wrong. Okay, still it is 6. It should be 5. Let's see what else. So we need to find upper bound of -1, which is 1. And sorry, lower bound of -1 is the first element greater than or equal to this. Okay, the first element greater than 2 should be 3. This index is 0, 1, 2, 3. This should be 3, right? We're getting it as 4, so that's the first wrong thing, right? And here we should have -2's lower bound is -2. 1's upper bound is should be this. So this is correct. This is correct. Right. So 3 minus 0 is 3. Here should be 3 minus 1. So let's see why upper bound is not working fine. Let's see. So if we try to do console.log upper bound on this array for the element 2, let's see what do we get. We're getting the index 3. Okay, here we are getting the correct index. Okay, interesting. We're getting 3. We should have got 3 here also.
lower bound, and let's try lower bound. Okay, now lower bound is 3. That's wrong. So let's see, are we making any mistake here? Okay, so what was the issue? Here we are by mistake calling n of I. This should be m of I, right? This should be m of I. And this should work now. Then see, we are getting 5. So this is the correct answer. Let's remove all the console.logs. Let's clear the console and run it. And we are getting 5. So we have successfully implemented this problem within the given time limits, right? So this is a very interesting, I would say, use case of lower bound and upper bound, with the fact that instead of like generating all the subsets, the whole array, we divided the array into 2 parts and then separately generated the subsets and combined the solution using binary search. We also learned that how we can generate subsets using binary numbers. That was also an added advantage here. So I hope you guys were able to get the logic for this problem. We are going to meet soon in the next set of videos. Till then, take care, guys. Bye bye, and thank you.